All right, actually I'm going to prop these doors open, so you got another few seconds. This gets too hot. Okay, so we're gonna get going. Okay, so a couple of administrative reminders. So assignment 1 is due a week from tomorrow. How many people have started it? I know some have started it because I saw some questions. I know at least one person who's not in this class says he started it. So, okay, that's good. Easy, hard, it's all going fine. It's all good except the licensing. So if you feel the pain of the licensing, trust me, I feel it too. I'm still trying to get a license for Questa so we could run Agilix in the future. Okay, but it seems like people aren't having too many problems with licenses, or they've been solved, the ones that I've seen, so that's good. Okay, readings for this week. So we had one that you should do, which means that could have questions about it on a test that weren't covered explicitly in lecture, so it's good to know about, and one that was optional. So good to read, you can submit a summary on it, and it'll be considered, but I promise I won't ask anything about it on a test that we don't talk about in lecture. Okay, so for next week, 2 papers that you should read, because you might ask questions about them on the test, and one that you could decide to read. Okay, so the first one is about, I think, a great paper by Microsoft about basically how they put FPGAs in every server in their data center. Their data centers are huge. So after they did this, maybe a couple of years after this, I was talking to Andrew Putnam, a senior engineer at Microsoft, asking how many servers is that anyway? And he wouldn't answer, but by binary search, it was clear it was about 1 million servers at that time and growing 30% a year, which is like a huge number of servers. These data center scales are unbelievable. So Microsoft has done 2 generations of how they put FPGAs into the data center. This was the first generation, which is interesting. The way they did it actually had a bunch of interesting features, but then they decided in the second generation they had a better way to do it, okay? And they've used this technique, they've kept upgrading the hardware, but the basic technique of how they interface things to the CPUs and make this available across the data center, they've maintained constant. So that's why this one is the one that it's kind of mandatory reading, you should read it. But this one's also quite interesting because they go into some more of the engineering development. And even though in the end they decide, 2 years later they decide this is a better way to do it, you can learn a lot by what they did the first time. So optional paper, feel free to read it, submit a questionnaire if you like. Yeah?
These are 3 separate readings, right?
They are 3 separate readings. So this one, how Microsoft puts FPGAs in their data centers today. Optional reading, how they did it first, which they decided was not as good an idea, but you can actually learn a bunch by seeing that. Sorry?
These are 3%, right?
Yes, if you did all 3 of these, it would count as 3 separate papers, 3 separate questionnaires. And if you go, no way, I can't do 3, then fine, do this one. This one we'll cover in class, so you'll kind of learn the key things from it anyway. But it's such a nice paper that I might be tempted to ask something about it on the test. It'll probably be covered in lecture anyway, but reading it is probably good for you, so I made it mandatory as well. And as I said, this one's definitely optional. Won't ask any questions about it that aren't in lecture on a test. But it's a really interesting paper, which is why I can't let it go. So I put it on there. Okay, so course concept map. So we talked about the basics of what FPGAs are, how to organize our thinking about computation with compute models. And what I'm going to talk about today is a somewhat grab bag of topics. So you can tell me in the course evaluations or after this class, did this work or not? But it's basically how do FPGAs compare to various other compute devices? So this is definitely going to be a lecture about breadth, right? Where we talk about all sorts of different compute devices rather than going really deep in any one of them. But again, a bit of an FPGA focus. Like what are the strengths and weaknesses of FPGAs versus other devices? But we're going to talk about CPUs, GPUs, DSPs, various other compute devices, but we're not going to go into incredible levels of depth on those because you can spend entire courses on each of those things. Okay, so you're going to make some fast computation. You've decided you need to make it using an off-the-shelf chip, so you're limited to programmable devices, right? You don't have the budget to go off and make your own ASIC. So what are your choices from a pretty high level? So the first thing you would think about is a CPU. CPU is the easiest thing to program, right? You can program it in high-level languages. So you should probably always think about a CPU first, and if it does what you need, it's probably the best choice. What does a high-end CPU look like? So it has a fetch and decode unit to bring in these instructions and figure out what they mean. And there's a wide variety of CPUs. This is a high-end CPU. So like a Intel Xeon or an AMD server chip, right? So something that's pretty fast, pretty fancy, pretty expensive. So it's got ALUs that actually do the execution. This is where you're really going to do your arithmetic. You have the execution context. So execution context is like, where's my state? So a lot of your state is in memory off chip, but we have some of our state on chip in relatively small register files and a bunch of caches, right? Like copies of recently accessed main memory data. Well, I guess this is our execution context, which is like our explicit register state. And then we've got our data cache so that we don't have to go out for our bigger state from main memory all the time. And there's a lot of hardware to just keep this busy. So this is really doing the work, right? It's our ALU that does the work. It is executing using the data that's in our register file and has to go to main memory. So we've got this data cache to insulate it from the slowness of main memory. And we have a lot of hardware that is actually not directly doing work, but it's basically keeping the CPU busy, right? What do we do next to this instruction stream? So all high-end processors now are out of order. And okay, so this is just a check of the audience. So does everybody know, how many people know what out-of-order execution means in a processor? Okay, how many people don't know what out-of-order execution means in a processor? Okay, so a few, so it's fine. So out of order, you write your program, if you're an assembly language programmer, in a certain order. Or more commonly, you wrote it in C or C++ or some other language, and a compiler turned it into machine code. But there is an instruction sequence, and the contract with the hardware is that it will execute as if those instructions all executed in order, okay? But if it executes all those instructions one after the other, obviously that can be slow. So it tries to overlap them. So with pipelining, that's the first approach you use. You have multiple instructions in flight. But you'd like to go faster still. So you may actually start sending out more than one instruction per clock cycle. So that's called superscalar. And then once you start doing that, you find that it's actually hard to find instructions that aren't waiting for data, right? Like that they're waiting for the output of some previous instruction. They're waiting for data to come in from main memory. They're waiting for us to figure out whether we take this branch or not, so whether or not they should execute. So we start getting with very deep pipelines, and with superscalar execution, we have so many instructions in flight that we could have in flight that we're limited by we can't find enough independent instructions, so we use out-of-order control logic. Out-of-order control logic means the processor actually has a window of instructions that it's looking at. For a modern processor, high-end processor, is probably around 100 instructions, but this window is slowly getting bigger as we throw more and more hardware at it. And it has a bunch of complicated control logic to basically say which of those 100 instructions are ready to go. Their data has actually arrived, so I can actually launch them. And it actually is launching them as soon as their data arrives. It's also launching them before it even knows basically what all your if-then-elses are going to resolve to. It doesn't actually know whether you're going to take a branch or not. So it's not 100% certain that it should actually execute this instruction. It just executes it anyway. Okay, so it basically is executing the instructions now not in the order you wrote them in, but in the order they're ready to issue. And it keeps track of, are all your inputs ready? And do I actually know all the branches that would lead to you actually happened, right? And if they don't happen, I will squash your results. They will never make it back into this execution context. They will only be kept in temporary storage. They will be thrown away. Okay, if that sounds complicated, it's because it is, okay? It's actually complicated to do for like 2 or 3 instructions. When you start doing it for like 100 instructions, it's like super complicated. It chews up like, it chews up like your mind. This is the first thing. Like just making this correct is hard. The second thing is it actually chews up a lot of silicon area. It chews up a lot of power. And as that instruction window gets wider, it keeps chewing up more and more. But that's what you need to do in order to keep finding more instructions to execute at the same time, is make the window bigger. Okay, so a bunch of logic there to keep the execution units busy. Another key thing is if we're looking at 100 instructions a window, the average code that a C or C++ programmer writes, usually there's only like 4 or 5 would be a typical number of instructions between branches. So if I'm looking at a window of 100 instructions, I actually have, like, where did these instructions come from? I have to actually guess whether I'm going to take various branches in order to decide which instructions I should bring in and put in that window. So that means I need to predict the branches. I can't wait until I've figured out the answer, because that means I'm waiting around too much. I actually want to be launching multiple instructions every single cycle, so I can't be waiting until all my branches are fully known, which might be like 14 clock cycles later, or even longer if there are dependencies. Okay, so these get big too. So the branch predictors turn into a bunch of hardware. I mean, the latest branch predictors are actually little neural networks, right? So they're actually learning what branches tend to be taken or not taken in your program as a function of various sort of features, various states in your program. So you can imagine that sounds kind of big, and it is, right? It's a bunch of hardware. You also are running a processor. A processor like this is usually running at 3 or 4 gigahertz. And the time to get a piece of data back from DDR memory is on the order of 50 nanoseconds. Okay, so you've got something that's got a clock period of maybe 300 picoseconds, and you need 50 nanoseconds. That's a factor of more than 100. Okay, so it's like over 100 cycles. So I can't wait for that. The data cache helps me, so I keep like recently accessed data in the data cache, but I need more. If I'm actually walking through big data structures in memory, the cache won't help that much. So I also need a prefetcher that's basically watching what's happening and guessing what memory I might need next, and trying to issue basically prefetch instructions that will bring it into the cache 100 or hundreds of cycles in advance. And that's also complicated. And it can also be wasted work, right? Like I might be wasting power bringing in stuff that it turns out I don't use. So all this stuff takes area, all this stuff takes power. Does that make sense? Okay, so basically, high-end CPU tries to maximize single-thread performance. What I get for this is if I write a single-threaded C or C++ or Java or whatever program, this is the fastest it's going to go, right? A high-end CPU will run that as fast as possible. We have such huge transistor budgets that this isn't enough to fill a die. I mean, if you made this logic big enough, I guess you could fill the die, but it would be a poor choice, right? Like you could maybe fill a huge die, but your instruction window might go from 100 to maybe 500. And you might get a little faster, but not that much. So it's not a good trade-off. So what they do instead is you put multiple cores on. So every core looks like this, and now you can explicitly, as a programmer, so with extra work, you can divide up your program into multiple threads, and they can collaborate. So you get more throughput, but you don't get better performance on one thread for having those cores. And a high-end CPU, this keeps going up, but typical numbers for high-end CPUs would be that you can get around 4 to 64, maybe you could get 128 cores now, which is a fair number. And then the other thing they do is you can see this ALU doesn't look that big compared to all this other stuff, and it's because it isn't, right? This high-end CPU spends most of its effort figuring out what to do, not actually doing it. To make it somewhat more efficient, high-end processors nowadays will also include SIMD units. So they can operate on, with traditional instructions that say add register 1 to register 2, but they'll also have instructions that say treat this large register as having four data items in it, this other large register as having 4 data items in it, add all the 4 pairs together and put them in the third register. And that SIMD has been gradually going up. So I'm going to show you this on another slide, but basically it started out, so we didn't used to have any SIMD. If we go back maybe 20 years, CPUs generally didn't have SIMD. You want to add numbers, you add them, 2 numbers that get added together. Then they added 4-way, then 8-way, and now a lot of these high-end processors will have 16-way SIMD. And what that does is it basically doesn't cost me more complicated control logic, because one instruction controls that whole 16 computations. It just does cost me more execute, right? Instead of one ALU, I would now need to do one of these instructions, 16 ALUs or 16 multipliers. But if I can use them, that's kind of moving more hardware into my actual execution. Does that make sense? Yeah.
Is it 16-way SIMD in each core?
Yeah. So this is like, yes. So these are two separate things. Every core would have like, say, 16-way SIMD, and then I don't know what to do with this giant die, so now I fill it up with many copies of that. Yeah.
And is the SIMD different than multiple issue CPU?
Yeah. So multiple issue is different. So multiple issue, I didn't put it on here, but so multiple issue is often called superscalar. Okay. Multiple issue means in one in one clock cycle, I have this window of instructions I'm looking at, and I actually can issue more than one. Okay? So that's kind of in this out of order control logic. I haven't explicitly shown it here, but those often go together. Like as I'm trying to issue more instructions, I usually start having all sorts of problems figuring out, well, what instructions are ready to go. So I usually put in this out of order control logic, and I put in multiple. I don't have to put in multiple issue, but they're often done together. Most of these high-end processors are, so the latest AMD and Intel server processors, which are generally the highest end processors of this type, they're about 6-way issue, okay? Like, so they're not all the same, but they've gotten up to about, in one clock cycle, they could issue, say, 6 instructions. On the average clock cycle, they won't, because even with all this fancy branch predictors, out of order control logic, et cetera, they usually can't find 6 instructions that are ready to go. So on average, maybe they'll issue like 3 or 4, but they built the hardware to do 6, because sometimes they can. Does that make sense? Yeah.
I guess could you borrow like some of the space from the data path to implement SIMD? Could you use that for multiple issues as well?
So yeah, you have an area budget, and you could basically say I'll do more in multiple issue, and I'll do less SIMD. Because if I make my SIMD really big, you go up to say 16-way, and that starts to hurt. Okay, like going from 1-way to 4-way, well, frankly, the ALUs and multipliers weren't that big compared to this other stuff. So going from, I got 1 multiplier to 4 in my execution path is not so bad. Going to 16, it starts to hurt, right? You're starting to notice it. You could go to 32, but you will start to notice. Like it's starting to become, I don't have exact numbers here for MSC, but it starts to become fairly big. But the cost to go from, say, 6-way instruction issue to, say, 12-way, like as your alternative, that cost is not linear, right? Like that, in order to actually make use of those extra 6 instructions, you have a huge amount of hardware, and you need wider windows that you're searching in, and therefore all of this out of order control logic gets more complicated. So yeah, to go from like 6-way issue to 12-way, it's not like that's twice as expensive. It's maybe 4 times, maybe 8 times more expensive. Like it's a lot. Does that make sense? And you might not get a good payback on it, because you still might not be able to, in most programs, find that many instructions that are independent, even throwing tons of hardware at the problem. Does that make sense? Now, the SIMD basically puts the problem back on the programmer, because the programmer had to essentially line the data up nicely. So it's either the programmer or the compiler, but compilers have not been great at this so far. They're getting gradually better. They have to line the data up so that one instruction can do the right thing. Okay? Whereas the nice thing about all this out-of-order control logic is you just write your C or C++ code and you don't think about it, right? It's just the magic happens. Okay, so let's talk about a graphics processor. So it's still a processor, right? This is not a hardwired circuit, but it makes some different design decisions. So it still has a fetch and decode, just like the CPU did, but it now has a whole bunch of ALUs. And the CPU doesn't really have just one ALU, it has a few, but the GPU has a lot of ALUs for every one of its compute cores. So they started out with essentially 8-way SIMD. That's what early GPUs would do. And this has been going up. So they're also increasing their SIMD width kind of gradually, generation by generation. And the idea is that, so what I've shown here is 8-way. So you fetch and decode one instruction, and it controls 8 execution units. So you've amortized the cost of your control. Notice there is no fancy out of order execution units here. Like there's nothing to try to figure out what to do next. The GPU does what you told it to do next. Okay, it's not as sophisticated at trying to figure out where do I go next. It has a different context for every one of these ALUs. So each of these have their own essentially register files that they can access. So, and it has a little bit of data that's shared across the context. But basically, it's distributed the state a bit more. There's some registers that every one of these ALUs are going to go access. So its programming model is that it's optimized for multi-threaded, for having lots of threads, lots of parallel work. It's not nearly as good if you gave it just one thread at crunching through it. But if you give it a lot of threads, it's basically built for parallelism, right? Each of those threads can come in and make progress on their ALUs using their register file. It requires more from the programmer and the compiler, like the combination of those two things, because it doesn't have nearly as much caching. It doesn't have the out-of-order logic to figure out what instruction's ready to go. So it basically what it relies on is that you divide your program into many, many threads. So you can basically do an instruction from one set of threads. They can go out all the way to main memory. It might take 100 clock cycles or 300 clock cycles for the data to come back. But while you're waiting for that to come back, you've switched to the next thread or next set of threads. They've all done a little bit of work, and then the next set of threads, and the next set of threads, and the next set of threads. So it needs a huge number of threads so that it can just keep working while it waits for long latency operations like going out to main memory to come back. Which is different than a CPU, right? CPU is optimized for single-threaded execution where it will figure out from this one set of instructions what to do next. So it's not nearly as good at getting one task done, like if you had one serial task, but if you can divide your task into a huge number of parallel threads, it's very good at that. So it's oriented for batch or throughput computing. Does that make sense? So this is like the very high level, how do these things fit together? Okay, so these things are not, they are stealing, all technologies steal from each other, right? Like that's actually good engineering. I mean, don't do it illegally, right? Like don't walk out of your employer with a hard disk. But if you're actually not paying attention to what the competition is doing, that's actually just kind of being arrogant, right? So CPUs and GPU and CPU architects do steal ideas from each other. So CPUs are adding more cores. They're adding more floating point units. They're adding more threads. So I already mentioned this. So if we go back in time, you used to have like just one core on a package. Now 4 to 64 would be typical. And the SIMD is getting wider. So it went from like only scalar CPUs to, if we follow Intel CPUs, they went to only integer operations. So integer operations are cheaper than floating point. So the first thing Intel did for SIMD is they said, well, integer operations, we could have SIMD, because it'll be relatively cheap to make multiple execution units for integers. And that was called MMX. It was basically for like video and sound processing. Then they added it for floating point, which is a bit more expensive, but the cores had already gotten bigger and had more out-of-order logic, so the percentage increase wasn't that bad. So they could do 4-way single precision floating point. So a single instruction could say, add these 4 floating point numbers to these other 4. That was called SSE. Then they went to 8-way. That's called AVX2. And they have certain chips, but not all. So that support something called AVX512. And that will do 16-way SIMD. One of those chips was Xeon Phi. Xeon Phi was intended for supercomputers. So it was intended for applications where you had a lot of parallelism. And when you have a lot of parallelism, like you're doing matrix operations, so the parallelism naturally fits into a SIMD paradigm, it's a good choice to kind of make simpler CPU cores and go wider on your SIMD. So that's what Intel did. And then some of their server CPUs will have AVX512. I think some only have AVX2. They have a small ability to switch threads. So who's heard of hyperthreading? Do you know that term? Okay, who has not heard of hyperthreading? Okay, so it's about half and half. Okay, so hyperthreading, like when you're building one of these high-end CPUs, you build a bunch of execution units, and then you build a bunch of logic to try to keep them busy. And I talked about the main part of that logic, this out-of-order execution logic and this instruction window. It's still not enough to keep all your instruction units, your execution units busy on average. So what most high-end CPUs have now done is they do something called two-way hyperthreading. What that means is in that instruction window, they don't just have one thread or one program. They'll actually have two, okay? And they'll look for instructions that are ready to execute from both of those. So it's essentially allows them to like mix instructions from two different threads or two different programs and keep the execution units more busy. Okay, so there's a few different ways you could do this. You could switch from one thread to another in one cycle, or you could even essentially interleave their instructions, as long as you kind of have tagged the instructions which thread it came from, so that you make sure you kind of put their data in the right spot. Yeah.
So what would be the main reason why they dropped hyperthreading now?
Have they actually dropped hyperthreading? Because I think they still got it in most of them. What's that?
They dropped it for a few generations until did. Now they're bringing it back.
Oh, that's interesting. Okay, so they dropped it, then they brought it back. I know it's in the UG machines, and it was in the generation before that. So I pay the most attention to the machines that we can actually run on. And in assignment 2, you're actually going to do some comparisons between GPU, CPU, and FPGA. So the CPU you're going to use has hyperthreading, which is part of why I mentioned it. That's a good question. I would guess the main reason they dropped it for a few generations is probably security. Because you probably, some of you might have heard of Spectre and Meltdown. Yeah, so hyperthreading made those worse by basically interleaving instructions from two programs, and then they found that there are ways, which I have to always go back and read the paper, so I cannot describe the ways exactly, but there are ways that they can leak information based on the timing of one program, which would vary depending on what the other program was doing in the cache. Hyperthreading, you can imagine, makes that harder, right? Where you have like two different threads that are being interleaved. It gives you some additional ways that you might be able to leak information from one program. Because Spectre and Meltdown were fundamentally figuring out, getting some information about what a program was doing based on timing, right? If you could tell it took longer, you knew whether something was in the cache or not. It looked incredibly painful, but the people who did this basically managed to turn that into, they gradually were able to figure out now information and try to crack your passwords. Which, if that sounds hard, I think it is super hard, actually. But they're pretty determined. So sorry, go ahead.
From what I recall, their reasoning was that they have like big cores and small cores. They were saying that to support like hyperthreading, it was taking up around like 40% of the area per core, and they just were getting like 40% more performance per core.
Okay.
So they decided to drop it.
But now they brought it back, you said, right?
Now they brought it back.
Yeah, so I guess they will now make the exact, maybe they'll make the opposite argument. I guess that is a valid argument. So like, yeah, CPUs are doing all sorts of things. So I'm talking here about a complicated core. They have done the big little technique as well sometimes of make one complicated core and pair it with one less complicated core. And for when you need less performance, use the less complicated core and it'll have lower power. So I guess that factors into this decision about hyperthreading too. Okay, but despite these changes, their main focus in a CPU is still, what distinguishes them is they want good performance on single thread. It's not the only thing they want. They also want to fit a lot of cores, especially in the server market, but they want to have good single thread performance. Their clocks are fast, 3-4 gigahertz. And again, in assignment 2, you're going to do some comparisons. So I'm going to give you the information about the UG machines. So these are Intel processors. They're this exact model. They're 8 cores. They're built on a 14 nanometer process. The reason that matters is when you actually start comparing efficiency between two different chips, you really want to know what manufacturing technology they're on, because otherwise you can kind of bury how efficient is the architecture of this chip underneath, well, was it just built in a better or worse process technology? So we're going to keep that in mind. They run at a highly variable frequency. So they can go up to 4.9 gigahertz, but it's hard to cool these high-end CPUs. So if you're doing a lot of work on all the cores, your clock's going to drop down quite a bit to kind of throttle the power and throttle the heat. So the frequency is a little bit complicated, at least 2.5 up to 4.9, but if you're using all the cores, you probably are not getting 4.9. You're probably getting 3 or so. And they can do SIMD. For floating points, they can do 16-way SIMD. and their power budget is, like their power limit is 65 watts. Okay, so that's just to give you a concrete one because you're going to do some comparisons on it. Yeah?
How did you find out how much SIMD was on the particular CPU?
I did LSCPU on the Linux machines, and it will tell you all sorts of information, and then you can also get like the microarchitecture code. So it's a little while since I did this, and then you can go look it up. So it was,
I tried to look it up, but I couldn't find.
I think what I did, the way I, so you're testing my memory because I did this 2 years ago, but you type LSCPU, it will tell you what versions of these SIMD instructions it supports. So yeah. So you can go basically look at, well, what does it support, and then go check what are those. Yeah?
I do remember some machines, some Intel machines, you do LCPU. It says it has AVX512, but it's virtual. It actually ends up becoming 2 AVX2 instructions sometimes.
That's interesting. Yeah, okay. So I should actually go check this to make sure it's not virtual, because often this would be 8x, right? If you don't get a very data-oriented Intel CPU. So I should probably go do LSCPU and just make sure it doesn't say anything like that.
I'm pretty sure it is AVX512 normally because I have to use it for different cores.
Okay, so you have used it. So you're validating the 16x. Okay, that sounds good.
But I tried it for a similar course, and I found that AVX512.
You're going to go check it then. I'm saving myself some work. So. Okay, so that was where our CPU is going. So GPUs are also adopting some CPU features. So there's a bit of convergence, but not complete. Okay, so this is NVIDIA's Ampere architecture. NVIDIA makes new architectures very fast. I think since Ampere, there's been Hopper and Blackwell. So there's 2 generations since then. And there's some information on one that hasn't shipped yet called Rubin. But things are not changing. I'll probably talk next week a little bit about Blackwell if there's interest. Actually, how many people would be interested in knowing how Blackwell, what is in Blackwell? Which I don't think I can tell you everything in it because it's just huge. Okay, so I'll put that next week because I'm going to talk a bit about machine learning next week. So this is not their latest architecture, but the new architectures are kind of just think of more of this to first order, right? So they are following a trend. Okay, so, but it's still pretty advanced. So it's 8 nanometers. It's actually a more advanced process node than the Intel processor that's in those UG machines. It's in UG 51 to 80. That's relevant for assignment 2 because you have to run on the GPU. So they call the equivalent of a CPU core is what they call a streaming multiprocessor. So that you can think of core. That would be the equivalent of an Intel core. Each one of these streaming multiprocessors groups 4 SIMD32 units together, okay? And NVIDIA is optimizing not for FP32 anymore. They can do FP32 and they can do it pretty well, but they actually put more effort onto smaller data types because it's generally good enough for graphics and it's definitely good enough for machine learning, okay? So they can do basically 128-way SIMD for FP16. They can't do SIMD that wide for FP32 because floating point 32 units are a lot more expensive. And they require twice as wide a port to your SRAM memories, so they're more expensive in 2 ways. So yeah, the SIMD would drop, and I'd have to go look at the data sheet to see how much it drops, but it would drop by at least a factor of 2 if you're doing FP32. So they're more optimized for FP16. You can think of this, it's somewhat like, not exactly, but it's somewhat like a 4 issue, like you can have 4 instructions, each of which was 32-way SIMD for this processor core. And the processor core is much simpler. There's no out of order, et cetera. It's basically execute the next instruction and rely on there being lots and lots of independent instructions, independent threads to get performance. It is more flexible. It's not quite like a 128-way SIMD core. It is more flexible than that because of the fact that we have essentially 4 32-way SIMD units with some independence. Not complete independence, but some independence. We have, instead of caches, we mostly have explicitly managed scratch pad memories. So the difference between a cache and a scratch pad is just, does the programmer decide what goes in it, or does the hardware decide what goes in it? In a cache, the hardware decides. The programmer is not usually very aware of the cache. With a scratch pad, the programmer is explicitly managing it, right? Deciding what goes in. So the scratch pad memories in a GPU are, first, they have very large register files. and the programmer explicitly manages what goes in those register files. Each thread usually is only using a few registers, but because there are many, many threads that are executing kind of interleaved, we wind up with a very large register file overall. And that's what these are. Okay, so this is like one of these streaming multiprocessors. So it's showing you've got these 4 SIMD units, and it's got 16,000 registers paired with each of these SIMD units. So it's got a lot of registers. And then we also have a shared memory here. And this shared memory is shared across all 4 of these SIMD units. And this shared memory is also usually managed by the programmer. Okay, they decide what goes in it. And that's the only way that you kind of get data in between these pieces of SIMD execution through this shared memory. Okay. They are adding some more general purpose features. So the first thing they can do is this what they call the L1, the shared memory or L1 data cache. So it used to always just be called shared memory, right? This was the shared memory that you could use to have essentially the threads within one of these streaming multiprocessors communicate. So it used to always be explicitly managed by the programmer. They now have the option for the hardware to manage it. So you can turn it into a cache by saying hardware manage it, and that's done to make programming easier. For most high performance uses, so I was talking to one of my former grad students at OpenAI, so he says they never turn this into an L1 data cache. They always use it as like the explicitly managed shared memory because they want to get performance. So they're willing to put the effort into writing these low-level machine learning kernels, and they want to know where their data is. So they use it as a scratch pad, but it's now possible for people maybe who are bringing up applications faster, don't need the best performance, they can use it as a cache. Then they have a bunch of these streaming multiprocessors. So in this particular architecture, they have 48 of them. Okay, so replicate that 48 times. That's like your 48 cores. Those go out to main memory, and before they go to main memory, they have an L2 cache. And in this particular chip, it's 4 megabytes, which is not that big compared to a high-end CPU. But it's more than GPUs used to have. We'll go back a few generations, they didn't used to have these second-level caches. And this one's always hardware managed. So this is basically, once you get out into the interacting streaming multiprocessors, it gets very hard to think of what exactly is going on. So they built this hardware managed cache to just try to reduce main memory traffic some, make things more efficient, and it isn't programmer managed because I guess it's just too hard to think about what the heck's going on. So that's a CPU technique, but they're not spending as much area on it because this wouldn't be as big as the last level cache in like a recent or even not so recent Intel processor. Yeah?
I just noticed there's another shared cache at the top. Is the same as the one at the top?
This one is the L1 instruction cache. Is that what you're talking about?
Oh, yeah.
Yeah, so that's instruction cache. So I didn't talk about that, but they're basically, they also have an instruction cache, but it's not quite as important. Does that make sense? Usually their instructions are somewhat repetitive given the applications they're working on. So they cache pretty well. Okay, so they run at a reasonable clock rate. This one, 1.5 to 1.7 gigahertz, which is pretty fast, but not as fast as a CPU. So they made the trade-off of let's get, in our power budget, we'd like more SIMD. We'll sacrifice some clock frequency. Their power budget is quite high. So in this generation, it was 290 watts, which is at least equal to the highest end CPUs, generally a bit higher. And that's continued, right? NVIDIA is basically pushing the boundaries of like how high can you, for GPUs that go into data centers anyway for machine learning, they just keep throwing more and more power at it. So the power budgets are huge. Used to be 300 watts, but getting bigger. And then they have one other thing that they put in here. So SIMD leverages, is very good for data parallel applications, right? One instruction controlling a bunch of units. A lot of graphics and machine learning, you actually can break many of the linear algebra components down into small matrix multiplies. And a matrix multiply has a lot of data reuse, okay? So you actually do n cubed computation with n squared data. So that means if you actually build units that can do matrix multiply, you can save a lot of traffic to and from even your register files, right? Because you can reuse the data a bunch. So they build small matrix multipliers, and the exact dimensions of them, I think, are changing from one architecture to the next, but in Blackwell, they look like they're about 8 by 8. So you now can send out instructions that go to these matrix multiply units, and that replaces a lot of SIMD instructions, because and a lot of data motion. So it's really useful in linear algebra and deep learning. So I guess if you think about this also as an example of like streaming hardware, like they're using the SIMD programming model, and they basically built a piece of streaming hardware, like matrix multiplication units, and hooked them into their processor. So you can see how these compute models they kind of show up all over the place, right? This is like a highly programmable ASIC. And when you dive down into how is it getting performance, on a key application of matrix multiply, they basically built some streaming hardware and hooked it up to their instruction stream. So compute models are useful, right? They show up all over the place. Okay, so I think somebody asked me a week or two ago about single instruction multiple thread versus single instruction multiple data. Okay, so we already talked a bunch about single instruction multiple data, right? Single instruction operates on many data items. And basically, either the compiler or the programmer had to get everything all nicely lined up. Okay, the data items are all in essentially consecutive words in some big register, or in consecutive words in memory. So it all has to be nicely lined up, and then the instruction can do 4 or 8 or whatever additions at once. Single instruction multiple thread it's very similar to SIMD. You're going to do the same operation to a whole bunch of data in parallel. But it puts a bit less burden on the programmer. So it has a whole bunch of threads operating in coordination. So instead of one instruction saying, do the following thing on 16 pairs of data, you have 16 threads that all are actually doing the same thing on different registers. And it turns out those registers are all nicely lined up. They're all consecutive, okay? That puts some extra burden on the hardware. The hardware has to look at those threads, see that they're doing the same thing, see that they're using consecutive registers, like 16-bit registers say, and say, that actually I can do all at parallel. I have 32 different execution units to do that, and I can see there are 32 threads that are all ready to go. They're all doing the same instruction. They all have their register numbers are nice and consecutive, so I can tell the SIMD units, all 32 of you can fire. Okay, so there's some extra burden on the hardware. They don't do this across, like, let's just go look across tons of instructions. They're just looking at these 32 threads and seeing, are they all doing the same thing right now? Because they're basically operating in lockstep. So it's a very limited window of what they're looking at, but they are basically doing a little more hardware management at runtime, which gives them an easier programming model. Does that make sense? Yeah.
So are you looking at like each thread, and let's say the common instruction that you're issuing is like an add, and you're saying, okay, like all these threads are doing add right now. Let me issue like a SIMT instruction. Is that how it works?
Yeah, and I can't actually say exactly when you get to the lowest level of the hardware exactly what they've done, but it is basically that. Now, they are optimized for the case where there are 32 of these happening at once, which means that they're almost certainly in their decode logic and et cetera, like they haven't really built 32 copies of everything, right? Like they've optimized it for the case of I found a whole bunch of these things that are the same. And the first one that I find is not the same, I'm just going to say, I'm done. Turn off all, I only found 8 things that are the same. The other 24, you turn off this cycle. Does that make sense? Like you're not going to go look for, are there other things I could put in there? It's like, does that make sense? But instead of finding one instruction that says do this on 32 things, it's like I will find 32 instructions, but they all better be right beside each other and have this very basic pattern. And if that happens, I will say, yeah, all of those, I can activate the execution units for all 32. And they can only really do the same thing. Like even the wires you're only going to send the wires out to control them such that they all can do the same thing. But there's a little bit more orchestration logic here that is basically figuring out, oh, there's only 8 things to do, or there's 32. Now the programmers and the CUDA programming language and their compilers and the way programmers use this, they work really hard. to make sure that the next 32 things are all the same operation with all the data perfectly lined up. So that's the way people try to use this. And whenever you get cases where there's an if statement in the middle, which is called branch divergence, or you don't get the data coalescing properly, people don't like that, right? Because they'll see their GPU slows down a bunch. And if you get a lot of that, it'll slow down below your CPU, right? So there's a break-even point where this just is worse. But if you've got a lot of parallelism, data parallelism, you can usually make it run very fast. Does that make sense? So yeah, it's similar, but they have done a nice thing here. Because this has made NVIDIA, their program model has been easier, right? I think it's always hard to figure out commercial success, how much it was technical success and how much it was being in the right place at the right time. But a key reason why NVIDIA has been so successful at the graphics market and now machine learning is their program model is like good enough, right? Like people can get performance out of it. And people can also get performance out of CPUs by writing SIMD instructions, but it has been harder, right? So I'd say this has added value. Yeah?
Does it mean to compete with NVIDIA, you need to find somehow maybe an easier way to program it, and also be a better programming model?
I think you need at least one of those things. You either need you need more performance, or more performance per dollar, okay? Or which includes performance per watt, because that's a big part of it. So you need to provide some value, and then your software has to be good enough that you get your job done. That's probably the most likely way somebody would challenge them. Another way you could challenge them is you have like good enough performance and your software is easier, right? And in theory, a CPU could do that, but CPUs have not been close enough in performance, and NVIDIA's done a great job of building these libraries on top of their GPU, so that even if the GPU itself might be harder, a more difficult programming target, it doesn't seem that way to a machine learning developer, for example, or a graphics developer. So you're going to have to be better at least one of those two things, and okay on the other one. Yeah, no, NVIDIA's an impressive company. So let's see. Okay. And yeah, so NVIDIA GPUs use single instruction multiple thread, and most CPUs nowadays support SIMD, okay, as well as their traditional scalar programming, just like add these two numbers together or multiply these two numbers. I mean, one of the other things that is interesting about the way that almost all CPUs have done SIMD is, okay, so I go back here. You see Intel, they had one set of instructions for MMX, then another one for 4-way SIMD for floating point called SSE, then another set of instructions for 8-way, then another set of instructions for 16-way. Each of those is like a different opcode, okay? So that means your binary is actually different. If I want to, so it means I don't actually get more SIMD when I go from one generation to the next unless I at least recompile my program. But often to get good SIMD, people had to actually write what are called compiler intrinsics, which means almost inline assembly, right? Because the compiler couldn't do it that well. And basically what you had to write is, what you have to write is a bit different for 8-way versus 16-way. So that's a burden on the programmer, right? You at least have to recompile your program, or you won't get the benefit of this 16-way SIMD, and you might have to recode some of these compiler intrinsics. It was, in retrospect, I think this probably was a mistake, right? Like they put it right in the opcode. It's kind of efficient for the hardware, but it removed one of the things that CPUs are really good at, which is that you can just run your binary on the next generation and it gets faster. That became not true in terms of getting more SIMD. And if you look at the way NVIDIA did it, because they said, well, just tell us there are just tons of threads, and our hardware will figure out which threads, they should be nicely aligned, that they're all doing the same thing at the same time, but then our hardware will figure out how many of them can execute. That gives them a certain amount of independence, right? It's like a little, it's been a bit more scalable in my opinion, right? They haven't needed as much tweaking. Now to get the best performance on the GPU, each GPU, you will still have to go micro profile and so on, but they can get some uplift if they add more parallelism without you rewriting your code. So it's been a little more clever that, in my opinion, that they didn't embed the amount of SIMD right in the opcode. Yeah?
So why doesn't, I mean, like from the programmer perspective with NVIDIA, just to use those GPUs, you kind of just need to use like CUDA, and CUDA does everything kind of like behind closed doors, right? You just tell it like, hey, like target the GPU and move all these matrix multiplication in the GPU. So why doesn't Intel or AMD kind of have like a CUDA CUDA equivalent for the SIMD units. So instead of programmers having to kind of like do the opcode.
Yeah. Well, that's a good question. I mean, so, okay, so the dominant way people have used it, like I said, is these compiler intrinsics. And those, unfortunately, have been specific to a certain SIMD. So you've had this burden. There is, there's a competitor to CUDA called OpenCL, which got renamed SYCL. So SYCL and OpenCL, as far as I can tell, mean the same thing. It's just companies and standards bodies love to rename stuff. That's the open source equivalent to CUDA. So CUDA is this kind of thread-based programming model, like data threads. You have lots of threads that are going to do the same thing on blocks of data. And now that's going to line all these threads up, and our SIMD hardware is going to be able to execute them at once. Okay, so that's the purpose of CUDA. OpenCL has the same programming model with like minor differences, but it's open. NVIDIA did so I actually thought, so I was part of a project. So one of the two people, so myself and one of my reports, Desh Singh, created a project at Altera to make an OpenCL compiler, because I thought OpenCL is the open standard. It's data parallel. We could make that map to FPGAs. And now we could like take this data parallel programming language and have this nice high-level synthesis tool that maps it to an FPGA, makes you a whole system. You know, we did it. I mean, well, I was part of doing the first part of it, and then Desh was the one who really saw it through. But it worked pretty well. And I thought the open standard would win in the end, right? Like CUDA, because it only targeted NVIDIA. OpenCL targeted, you know, AMD GPUs. It targeted CPUs. We made it target FPGAs, so it should win. NVIDIA did a great job of improving CUDA so that CUDA always had better performance and was easier to program. And therefore, they got more developers developing for CUDA, and they built libraries above CUDA, which gives CUDA a huge momentum, right? So it's not just about how good CUDA is, and CUDA is good, but it's, at this point, you have all these libraries for graphics and machine learning and et cetera on top of CUDA that are actually quite hard to replicate. So it's an interesting example. Usually the open standard, if it's good enough, will win because people don't want to be locked in. So the other way you could undercut NVIDIA is undercut their profit margins. So NVIDIA actually, no, I'm not kidding. Like NVIDIA is basically like, they behave like an FPGA company now, okay? But like a huge, incredibly successful FPGA company. What I mean by that is I think I told you the story about visiting a customer and you know the sales force had just made up a price for the chips and charging them $50,000 each. This is a few years ago. I bought like GPUs for some machine learning my group was doing. And the server class GPUs to do this were $21,000 each. And my grad student who was figuring this out knew a lot about GPUs. So the consumer class ones that had a little bit lower performance, you know, maybe 30% less performance, were like $1,500. So you kind of know what the profit margin is. You go, I know you could build this profitably for like something like $1,500 or $2,000, but you want to charge me $21,000. They basically made the cooling solution, like the heat sinks and the fans, of the consumer ones so they would not fit in a server. So they're basically segmenting their market. Like you are in a server market, looks like you might be doing machine learning. We think you're price insensitive, the price for you, 10x. It was super annoying. So we bought the consumer grade ones and basically just hacked the cooling solution. Like just took tin snips and we made it work, right? But like, you know, a data center is not going to do that. Like that. Anyway, the reason I say that is basically there actually is an opportunity there if you're good enough. Of NVIDIA's profits are extremely high. They're extremely high because they're actually not, they don't have enough competition, right? The only way you can sustain profit margins that big is you're just running somewhat unopposed at the high end. And they are. So yeah, that's, if you get close enough, you can make a very good business by just undercutting it. I'm just assuming you got a business ready to go. So I'll invest in you after this. So, I asked another story in that domain is I asked one of my friends who's on the former colleagues who's on the TPU team at Google. This is a few years ago. He'd just given a presentation on Google's tensor processing unit. So that's their machine learning accelerator, which basically goes further on the streaming data hardware side. It has an instruction stream, but the instruction stream is mostly controlling a giant matrix multiplier, right? So they basically moved more of the problem to streaming hardware because they put most of their hardware budget in like a big matrix multiply unit. And then the instructions kind of orchestrate data for that and figure out how to use that to do even bigger matrix multiplies. So I asked them, like, is this worth the NREs you guys are spending? Because you'll be spending like at least tens of millions of dollars a year, probably hundreds of millions of dollars a year on to develop these chips and systems. are you that much better than a GPU? And he said, we don't have to be any better than a GPU because we just have to charge a lower profit margin because Google buys, he gave me the number, it was like billions of dollars worth of hardware. So he goes, if you basically cut out, you take an 80% profit margin out and bring it down to like just what is the cost or some internal profit margin, that will pay for those 100 or 200 or 300 million dollar NREs many times over when you're into the billions of dollars of hardware. So, which in retrospect is obvious, but it was interesting. I was thinking like an academic, like you must be better, or what's the point of doing it? And his point was that we don't have to be any better, we just have to be cheaper. And we can be cheaper just by not charging such a huge profit margin to ourselves. So, yeah.
Yeah, so like one comment on the SIMD instruction CPU, the libraries like MATLAB and the NumPy libraries in Python, they use those.
Yes.
And so that's why they always be faster than you adding a bunch of numbers.
Yeah, and that's a good point. So it's kind of like the layers above CUDA. As long as somebody, like NumPy, goes and figures out how to use these SIMD instructions, then you get the benefit of them if you use that. So that's true. Okay, so DSP processors. So we don't talk about this as much in academia, but this is the last major class of processors. So they're optimized for signal processing. They tend to have lower power budgets. They have simpler control. They're focused on loop processing. They're optimized for multiply accumulate. And they don't worry too much about being quite as general purpose. They often will have separate memory spaces for programs and data. So they're essentially intended for more embedded purposes. Again, like one of the places you might find them is you open up a cell phone base station. You can find a bunch of DSP processors in there. So they're related to the other processors, but they don't have the kind of huge power budgets of a GPU, and they don't have the huge performance targets of a GPU. They're optimized for kind of being efficient at a somewhat smaller scale. This is one of the most successful DSP processors. So it's a TI C6000 series. So they have a whole bunch of chips in this series. So it's a high-end DSP. So there are like low-end DSPs. There are high-end ones. It's a VLIW architecture. So it has 4 address or memory units. So these units basically just are calculating addresses to go figure out where my data is. It has 2 general purpose ALUs for adding numbers, et cetera, and 2 multiply accumulate units. That multiply accumulate unit can do a little bit of SIMD. So it can do either one single precision floating point, or it can break its execution units up. And so with 32 bits of data coming in from the register files, it can interpret that as 2 16-bit numbers and do 2 16 by 16 integer multiplies. And to make it more efficient, they also partition their register file. So what that means is they have basically like 8 execution units here. Some of them are about getting data from memory, like load and store units and memory units and data path units. And basically these 4 are connected to half the register file. And these other 4 are connected to the other half of the register file. And then there's one, so that means we have like basically we only need 4 ports, right? We need 4 things that can read from this register file, 4 that can read from that register file. Now, it could be hard to program if there was actually no way to get data between those 2 halves of the register file. So they add one more port, which is basically for moving data. So they wind up with 5 ports. It's cheaper to make a register file with 5 ports than with 8. Now, it's a little bit less flexible, but they found this a good trade-off, right? So they've kind of made their storage less centralized by partitioning their register file this way. Remember we talked about whenever you have central storage, you put everything in one spot and build lots of ports to get at it. It tends to be high area, tends to be high power. So this is a way that they've made that more efficient. But it makes it a little bit harder to program. In some of their later and higher end DSPs, they add more SIMD. So they basically take those multiply accumulate units, and instead of doing one single precision floating point, they can now do 4 with one instruction. Or they could do 8 integer operations or fixed point operations. In this DSP processor, you can explicitly manage the memory. So they have caches or scratchpad memories, and you decide what they are, right? So you can say, I want to manage them. I turn off all the hardware management, or you turn it on and you let it be used as a cache. People often use them. So in signal processing, you often want very controlled latency. Like if you're doing audio processing or wireless signal processing, it can be an issue if your latency is jumping around because you don't want to drop any data, you don't want any gaps. That's another reason that explicitly managing the data can be useful because it's very deterministic. So they have first level instruction and data caches, 256 kilobyte level 2 cache. So basically these are not nearly as big as like a high-end CPU. They're built for efficiency. And they have a lot of variants. So depending on what you want to do, you can get a DSP processor in this series that doesn't have any floating point. So it only has the integer units. So that's you're doing all your processing in fixed point, which a lot of signal processing engineers will do for efficiency. Or you could get one that has floating point. You can get multi-core versions. So what I talked about was essentially one core. If you need more performance, you could get up to 8 of those on a chip, but it'll cost you more. And they build in also a lot of hardwired accelerators. So if you go look at their catalog, they have a whole bunch of different variations. And one of the variations is essentially they've added like hardwired accelerators. So it's like streaming data flow style accelerators for various things that will be important in signal processing. So fast Fourier transforms, Viterbi decoders, et cetera. You could do that on the DSP, but if a large part of their customer base is doing this, they will go and build an accelerator for it, stick it on one of their chips, and sell it to you. You can also get ones that incorporate an ARM processor plus a DSP to kind of run your whole system. The DSP could do your control processing, but it's not optimized for it. It's not optimized for single-threaded performance. It's optimized for essentially power-efficient data parallel performance. There's a wide range of power, depending on which of these variants you choose, but it's a lot lower than either high-end CPUs or GPUs. It's like 1 watt to 20 watts. Okay, so as to summarize all that, so all these things, DSPs, CPUs, GPUs, they're all variations on processors. They differ in their power budgets. So CPUs are like 100 watts and up. Like the power budgets keep going up, right? So it seems like there's hard to bound these. But then for a high-end CPU, they certainly wouldn't be less than 100 watts. They're often now quite a bit more. 300 watts used to be like the number for like high-end GPUs, but now some of the machine learning ones are going liquid cooling and much higher than that. For DSP, much lower, from less than a watt. So some of them will go down to tens or hundreds of milliwatts, up to like 20 watts is like a really high power, beefy DSP. And FPGAs are, the low end are quite a bit less than 20 watts. So the really low end are well under a watt. And the high end could be maybe 100 watts. But they don't really go up into these 300 watt territory, and certainly not like the kilowatt territory that NVIDIA is now exploring. There's some convergence between them. So they're sacrificing some performance for ease of programming. So there's more caches going into DSPs and GPUs to make them a bit easier. FPGAs and DSPs have put floating point in, which they didn't used to have. Everybody's leveraging SIMD. Okay, so DSPs leverage it a little. CPUs have quite a bit. And GPUs have a lot, but it's organized as this SIMD. And there's some divergence, right? So there's a reason that we still call these things different names. CPUs still spend a lot more area on single thread performance. One sequence of instructions, how fast can I run that? GPUs tolerate latency by having a huge number of threads that they can switch between. And DSPs basically rely on explicit scheduling and the programmer moving the data around. Generally, the programmer is saying, bring this from main memory, lock it down in this scratch pad, et cetera, to be highly efficient, to be highly power efficient at a lower power budget. Okay, FPGAs rely even more on explicit scheduling and data movement. So you can build anything in an FPGA. So you could build a bunch of hardware managed caches, but it's probably not a good idea. Because you're building it out of this programmable silicon that's less efficient, if you start building things that exist in for example, high-end CPUs and are expensive in high-end CPUs, it's probably not a good idea. So in an FPGA, normally you build a custom and highly distributed memory system, right? So your data is close to the execution unit, it's highly optimized for your problem. You can create a custom processing pipeline. Where their advantages are biggest are small data types. Because if you have small data types, then the fact that they don't have to have an instruction stream is a bigger win. because there's not that much energy and that much area being consumed by the execution because the data types are small and your adders get smaller and your multipliers, et cetera, get smaller as your data types get smaller. So it helps them. They're good at integers. Integer computations are also easier and cheaper than floating point, so that also plays to their strength of you can put all the area into the computation and not into like the control logic and instructions. Typically been weaker at floating point because floating point takes a lot more hardware and tends to be somewhat bigger in terms of precisions. But that's gotten closer in recent years. So Altera with the ARIA 10 FPGA that you're using in assignment 1, they added hardened floating point units to the DSP block, which greatly improved the efficiency of floating point in an FPGA because it went from you had to do a lot of it in the programmable fabric to you could do it all in the DSP block, where it's basically as efficient as an ASIC. And you can, when I was at Altera as we did this, it wasn't clear it was a good idea because our customer base at that time tended to be signal processing engineers who were very good at optimizing. So, and if you're really good at optimizing, you're like, why do I need floating point? I can do enough simulations to work out what the range of my numbers are. I can do it all in fixed point. It'll be more efficient. So there was a group of people in Altera who said this is foolish, right? Because the people who will put a design in an FPGA are hardware engineers who are quite skilled, right? If they're not very good at getting efficiency, they're not going to use an FPGA. So you're kind of building something and it doesn't match the customer base. The customer base is going to do it in fixed point. But it turned out that, well, that's still true. Lots of people do things in fixed point in an FPGA because it's still more efficient. There was a class of new applications like in radar and scientific computing where it was kind of too hard, right? There was too much work, or there were few people who knew how to do it, or the dynamic range was large enough that they did want to do it in floating point. And how you can tell it's a good idea is Altera kept it in all the generations after. There have been 2 generations after ARIA 10, and they both kept floating point. And Xilinx also did it. So in Xilinx's most recent family, they put hardened floating point in. Basically, when the 2 major FPGA vendors both put something in, then it's really hard to get out. Okay, like when one of them puts it in, it might be a mistake. People are also actually kind of nervous about using it if they might want to flip between vendors. They don't want to get locked in. Once it's in both, it means both companies think it's a good idea. Maybe it's still not a good idea, but at that point, it's kind of hard to get out. So, and then it's the only platform that doesn't need to interpret an instruction stream. So it is still pretty different than those other ones. Okay, with that, I'd say we should take a break for 10 minutes, and then we'll go through some of the readings. Maybe I'll ask if there are any questions first, and then we'll take a break. Yeah?
I did have a quick question about, so you said that a lot of the power in CPUs are all from the instruction look-aheads and all that other fanciness that's going on, not the compute.
I mean, it's mixed. Basically, the architects will try not to have it all be, like that's part of why you have SIMD, right? Part of why you have SIMD is as the power budget starts becoming all about control logic, people notice that and go, what can I do, right? That seems kind of crazy. So you can say, well, I'm going to make more cores instead of making the control logic even more complicated. And I can make more execution units, but I have to control them in a simpler way, like using SIMD. There's also a lot of power that goes into data movement. So that's the other thing. So if you look at the execution of a CPU, they do spend a lot of energy on those out of order control logic, et cetera. There's also a lot of energy that goes into data movement.
Gotcha. So my question was then why is the GPU so high if they don't have any of that? And the reason is probably because of all that data movement.
Well, it's also they go for very high parallelism. So, I mean, yes, there is a lot of data movement. So you're going to see this when we go through some of these peak numbers. But basically, GPUs build very high memory bandwidth because their programming model allows them to tolerate high memory latency, so they can execute straight out of main memory. But that is high power. Building high memory bandwidth basically costs a lot of power. They also, by simplifying their control logic, they basically take all that area and power budget and turn it into execution units. So that's how GPUs get to very high parallelism rates. In recent GPUs, it's just been shown that the more, like machine learning, if you basically build something with more performance, people will buy it. So that produces pressure to like, okay, can we put more execution units on by basically building bigger dice, connecting them with interposers. And Blackwell does both those things, right? Like, so reticle limit dice, so at the maximum you can make, and then don't do one of them, take two of them, put them in an interposer, right? So you have huge pieces of silicon that they're clocking as fast as they can, and they're clocking them beyond what you would usually be able to do because it's too much heat, but then they water cool them. That's all super expensive, right? Like none of that is a cheap technology, but people will pay lots of money for it. So it's like, well, we'll do it. So they've kind of pushed, for a long time, people didn't want to do water cooling as like a common solution because it is technically more challenging and more expensive, but that barrier's been broken in the data center. So, yeah.
You mentioned for Blackwell they have interposers. I know they have HBM, so they have stacked memories with the interposers, but are you saying they also have like the actual GPU chip? There's two chips that are interposing?
Yeah, so they've got, this is maybe getting on to other things. I'll try to put a summary of Blackwell in for next week, but basically they have HBM all over the place on it. And I think it's like 6 channels of HBM in Blackwell. So that's like an stacked memory technology on an interposer. And we'll talk later about interposers later in the course. So if you kind of go, I don't know what that is, we will talk about them later. And then they actually have two dice connected by an interposer. I'm pretty sure that's in Blackwell. I've also been looking at Rubin, so I have to make sure I don't get confused about which generation. Rubin doesn't exist yet as a product, but it does exist on their roadmap.
The first GPU that utilizes 3D.
It's not truly 3D. I mean, it's
The interposer.
so interposers, like you often call it 2.5D technology, right? So you can basically integrate multiple pieces of silicon, but not so much vertically, right? And then HBM is kind of stacked memory on an interposer, so it's also kind of 2.5D. So they're not quite 3D, but they're not quite 2D either. Anyway, so I guess a summary of that though too is if you take a lot of silicon, you start stacking it funky ways, you can burn a lot of power in a certain area. So that's why they have to go to liquid cooling too. Okay, so let's take a 10-minute break and then we'll be back. Are we online? Thanks. Okay, so this is the first reading, or maybe it's the second reading, but it was the optional one, because this one's like not too hard to understand. So it's from a few years ago, but I haven't seen one that is doing exactly the same thing. They basically take a broad class of devices and do essentially guaranteed not to exceed like peak throughput calculations, which have lots of potential issues, but they can still give you some insight. So yeah, this paper is a max performance comparison. So they basically define a few things that interest them. So one is they call computational density. So how much compute can I get done in this device if all the data is on chip? How much compute can I get done in a watt? So most devices are power constrained now, and power is a big part of your operating cost too. So compute density per watt is important. And then on and off chip memory bandwidth. So they worry about those things as well. So those are the things they're trying to bring into their performance comparison. Okay, so what they did in this paper is they wanted to compute a bunch of peak numbers, like guaranteed not to exceed. So what they did in FPGA is they focused on integer operations. They build one matrix. Well, this is how they did the integer operations. They didn't just do integers, but they would build a multiply and an add unit. They would measure how fast that would run, and they would replicate it until the device was 85% full. So they're not trying to build a full application. They're just saying, let's assume it's got lots of multiply adds. How many of those can we build? They left 15% of the area because they still need some control logic, some steering logic, some logic to talk to the IOs. And then the other thing that is they made sure that they could keep this execution unit fed. So so they have to have like enough internal memory bandwidth to feed it. If they don't, they'll say there's no point in building all those units. They'll be limited by the internal memory bandwidth. So they took, for example, if I take for example one of the devices they looked at, this Vertex 6 device, when they're doing integer 32 operations, they found that they could fit 968 multipliers and 969 adds. So they'll take, the limiting factor is the multipliers. They'll say I could get 968 of these multiply add units in. They could run it at 296 megahertz when they just have one of them. So they assume they can maintain that as they keep filling the device up. And then they check, can I actually feed data to this? So they basically, let's see if I can actually draw on this or not. Maybe I can't. Okay, maybe I'll draw here. So what they've done is they basically have a multiply, they have an add, and I can't remember if they put these in a cascade or if they put a muxing around them, but they basically have to feed these. So they basically say, okay, I need a RAM feeding each one of the input ports of this unit. Okay? And this would be like an accumulate. So it would be an add, and it would keep its data. So what they check is that they have enough memory ports. Basically, can I read from this memory and it can provide 32 bits of output? Can I do an independent read of this memory and it provides 32 bits of output? So that's what they need to keep this 32-bit multiply add unit fed. When they calculate, there's a lot of block RAMs on this chip. So they go, okay, if I build a memory on each port, they have to provide 32 bits of data every cycle. I can do that, and in fact, I could build 1,064 of these units, right? These RAM pairs. So they're not limited by the on-chip memory. So they basically say, okay, I can fit 968 copies of this times 296 megahertz, so I get 287 billion operations per second. So what do you think of this methodology? They do this for the FPGA. They do something similar for processors and GPUs. They essentially always, they look at what is its peak throughput in terms of operations, and that you have to have enough memory bandwidth from like the lowest level of the memory hierarchy, like the L1 cache or the register file, etc. So they do this, the part of why they follow this methodology is they can essentially apply it to really different things, like DSPs and GPUs and so on. But it's always take the most local memory and how many operations we can do, figure out if we can keep all those operation units, execution units fed. If we can, that's the number. So what do you think of this? Yeah?
Feels somewhat arbitrary. So why 85%? Could have just about 80,
Yeah, so you're saying this 85%, where'd that come from? It's not entirely clear. I think it comes from their heuristic of they've designed some of these systems and they find if I leave 15%, that seems kind of reasonable. But you're right, there's not a lot of precision on this.
And then also the fact that it's just like a multiply and add. We're rarely going to use FPGAs for that use case. Because with any application, you're gonna have more complex. You're gonna want to do more complex things. And
Yeah.
you probably really want to know when I do this complex operation. That's when I would care about the performance rather than I just do a multiply and add.
Yeah. Okay, so you're not sold. Okay, and you're right. Now, multiply add is probably not an unreasonable thing for like signal processing, for example. Like it tends to be the dominant operation, but it's not everything. So this probably captures an important part of some applications, but not all. Any other thoughts? Yeah, what do you think?
I feel like this is also like just rather unfair for CPUs in particular and variable for GPUs because they were designed for
So why do you think it's particularly unfair for a CPU?
because you're essentially looking at the throughput.
Yeah.
That's the most important factor.
Yeah, so they are only caring about throughput. They don't care about latency. So it's not focusing on like, the single-threaded performance that a CPU is optimized for. Yeah. 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 Yeah, okay. So I'm just going to repeat that. You're saying it's only internal memory. You're often going to be bottlenecked by external memory, which is true. I will say one thing in their defense here. This is just the compute part. They also then go and look at external memory bandwidth. So they don't kind of combine everything into one metric. They essentially take a few different kind of peak performance curves. One of them is just if I have the data on chip or could get it on chip, how fast can I process it if I'm doing multiply accumulates? But you're right. That would not capture the external memory bandwidth limitations, which they have to do separately. Yeah?
Like assuming the Fmax for one block is going to be the Fmax for the whole chip, that kind of seems a bit too reductive.
Yeah, so this is probably a bit optimistic. I mean, it's unlikely the Fmax is going to go up, right, as you fill the device. So it could probably only stay the same or go down, and it generally will go down some at least. So there's some optimism there. 15% is a bit arbitrary. Probably is a little on the optimistic side. right? It's hard to say. If your control logic's really simple, that might be fine. But a lot of FPGAs, as you approach 100%, you do actually start to lose like a reasonable amount of performance, so you might not want to push it too far. I would say, though, that those numbers, that probably doesn't change their overall. I mean, it's fundamentally still limited to how much multiply accumulate can I do when there's lots of independent operations. But it probably doesn't change things enormously. Maybe they lose 20% speed as they scale it up. Maybe this should have been like 25%. Okay, so now I'd knock all their numbers down by 25%, but I wouldn't knock them down by 10x. Yeah?
The one thing I don't like about this is that they're kind of ignoring all the IOs of the chip. They're just saying we're going to fill the chip to the max and a bunch of compute units inside.
So they will get to that later, though. They do it in like a separate thing. Yeah. Sorry, go ahead. No, sorry, I thought you were done. So.
No, but I think it would make more sense to use like a systolic array or something similar, where you just have a huge systolic array where you would just have multiply accumulates.
You could do that. What they're trying to do in this paper, there are lots and lots of papers that basically take the following system, and they basically, the good papers will say, let's put it on an FPGA, because that's the main thing I want to target, but now let's also compare to a CPU and a GPU, and that's the right way to do it. The problem with it is it's incredibly time consuming. Like if they were to do that for like, ideally you do it for, a bunch of applications, like 15 or 16 applications, and you're gonna see they try to do this now across a bunch of CPUs, GPUs, FPGAs to look for, let's just get some broad trends. If I took like 16 applications times like 20 compute devices, there is no one here who wants to do that PhD, right? Like that is the 100-year PhD. So there's a practicality problem with that one too. Did you have a comment back there?
Yeah, I guess this could be good for comparing between like the same, like generally the same class. Like for marketing, right? The green line goes up, so there's a lot you can do to make the performance always like go better with each generation, and it's a number you can put in this slide.
Yeah.
Very nice number.
Yeah, so it's a guaranteed not to exceed. So definitely you want to have a lot of caveats on this, but I think it does still give some insight. Yeah.
The other thing I think of is you don't account for any overhead that could actually, like compute overhead, in the sense that I guess there's mentions of I/O and memory, but you also don't account for, let's say on CPUs, there's the fetch decode, like the pipeline, whereas this you're only looking at the FPGA by nature is just a streaming device. I guess if I'm looking at the ones that also care how fast is like an instruction to execute, like without the overhead versus.
When they go to the CPUs, I mean, they do the same optimistic numbers for a CPU. Like when they give like how much can a CPU do, they basically go max SIMD, max clock rate, all cores executing. Do you know what I mean? Out of like first level, I can't remember if it's first level cache or register file, but basically a similar guaranteed not to exceed, right? Like you've perfectly blocked your data, you've perfectly parallelized it, what could you possibly get? So it's kind of optimistic on both of them. Okay, so all valid points. So you do not want to take this as like, the be all and end all. It is like part of a roofline plot. It's like not guaranteed not to exceed. Okay, so this is a bunch of processors. So they've got gray is, what do they get for basically gigaops for int16, int32, single precision floating point, and double precision floating point. And they do a bunch of different CPUs. So these are basically x86 CPUs. This is a relatively high performance one. These ones are lower performance. This is a like many core. So they call it many core. So like Xeon Phi, which is like an Intel CPU that's kind of targeted for lots of cores, really wide SIMD. So a more throughput-oriented CPU. DSPs, so some of the DSPs that I just talked about. GPUs, so both AMD and NVIDIA GPUs, but a few generations ago. And then these hybrid ones basically are mostly DSPs plus ARM cores and one GPU plus ARM core. So I guess the main thing you can see is some of them benefit a lot if you go to smaller operand sizes. So like this AMD CPU basically gets more SIMD if you can go to int16. That's just the way the CPU instructions work. So it does better in int16 and int32 and less well as you go to single precision floating point and double precision. The DSPs are much lower performance. They target lower performance targets. They have a similar property of like the smaller the data type, like int16, they're quite a bit better than int32, which is better than floating point. The GPUs, at least of this generation, it wasn't as big a difference. They actually were optimized for single precision floating point. So some of them, their highest, like the AMD ones, their highest performance actually occurred with single precision floating point, and they basically didn't care that much about the other data types. The NVIDIA ones, their double precision floating point was really bad, because GPUs don't emphasize that. But their single precision and integer was pretty much the same, because at that time, at least, GPUs were doing graphics in FP32, so they built as many FP32 units as they could. So I guess I'll talk a bit about Blackwell next week, like NVIDIA's latest GPU. It would be a bit different, because machine learning is very friendly to low precision formats. So in the latest GPUs, they do quite a bit better if you go to smaller data types, just because they divide up their data path and increase the SIMD width, and increase basically how many operands can be fed into those matrix multiply tensor units. So it'll be a little different in those. Yeah?
Did they pay attention to the node number? So for example, all of these hardware platforms have the same node number?
They're not exactly the same. They're within, my recollection from reading I read the paper a couple of years ago, I should have refreshed my memory. They're not all the same, but they're usually similar, okay? But there is some, you're right, there is some difference in process technology between some of them too. And I paid most attention to that for the FPGAs. I can't remember for these ones. Okay, so let's look at what the FPGAs look like. So the FPGAs have a very strong trend of you use smaller data types. So this is int16, then int32, then single precision floating point, then double precision. So a very strong predictable trend of if you go to a smaller data type, you will get considerably better performance, because you're basically building hardware on the fly. Okay, so it's, and that would even be true, you know, if you did int8, int4, etc. You don't have as many breakpoints in an FPGA. You have a few breakpoints because of what the DSP block can do, but in the programmable logic, basically the smaller you make your data types, the more efficient it gets. And let's see. Yeah, so let's see if I have any other items to point out here. Okay, so your question on process technology. So let's take, so this is Vertex 6, this is Vertex 7. There's a process technology gap between these two. And you can see that you get more performance out of the Vertex 7, so it did get a significant gain, which primarily, these architectures aren't that different. So primarily this was due to process technology. So yeah, you do want to correct for process technology if you're trying to get the right performance numbers. Okay, so that was like compute density. What about compute density per watt? So for what they called the fixed function devices, which are like the DSPs, the CPUs, the GPUs, they basically use the max thermal dissipation spec. So all those chips published, this is the maximum we'll ever dissipate. And to hit that, usually they have to throttle their clock frequency some if you're actually doing a lot of heavy lifting nowadays. FPGAs is actually a lot harder to calculate power because you can put all sorts of different circuits in them, so you can have wildly different power numbers depending on what you're doing. So FPGAs usually don't quote like a maximum thermal power limit because they don't actually know what you're going to do with the chip, right? So it's very hard to give that. So the total power is the dynamic power plus the static power. The static power doesn't change significantly based on what you put in the chip. Okay, it's basically a property of the chip itself and its process technology. It can vary a fair amount from one chip to another because it's strongly dependent on the threshold voltage. So if you get a little bit of a faster chip with a lower threshold voltage, it has more static power. So if you measure one chip, you've only got, if you want to know static power, you actually have to measure a whole bunch of different chips. But you don't really need to measure a lot of different designs. It doesn't vary much with different design. So usually you just take the specification from the company, right? So the FPGA company has a static power spec that'll be built into their tools that they guarantee it'll never be worse than this, because if it is, they already threw the chip away. They won't ship it to you. The dynamic power is a strong function, not just of the chip, but also of your design. And the dynamic power everybody builds everything in CMOS for many, many years. And CMOS only dissipates power when you switch. okay? And when you leak. But when you leak, it's in static power. The switching power is basically you're charging and discharging the capacitance of all the wiring and transistors. And the formula for that is, it's just if you go back, you can derive this yourself. You want to use your electromagnetic skills, right? So you can integrate what is the energy to charge up a capacitor. And it's 1/2 CV squared. And you do that every clock cycle where your logic value changes, okay? I mean, technically, you put half this energy, you put twice as much energy in when you're charging it up, and then you lose, well, basically, it turns out that half this energy is going in when you're charging it and half's coming out when you're discharging it. So you don't really care whether it's like a positive, you're going to a positive value or a negative value. You just say, if I change value, I will dissipate this much power, the energy that it takes to charge a capacitor or the energy that comes out when I discharge it. So this capacitance is a function of like the FPGA architecture and process technology. You know, how many LUTs did you use, how much programmable wiring, how good is the programmable routing, et cetera. The voltage is a property of, again, the chip. What voltage should you operate it at? You choose the frequency, and this alpha is hard to say. This alpha depends on the design. It's like, how often does a signal switch? Okay, so they basically take the device, they say it's 85% full of these RAMs plus multiply add units. They take the maximum frequency, which they already got, it was like 296 megahertz, so they know all those things. And then they don't actually have an application, right? Like they don't have a complete design. So in assignment 1, you're actually simulating your complete design to basically figure out this. You know the frequency, but you're figuring out the alpha. Like how often does every signal toggle? So they assume that it toggles every single clock cycle, like every signal in the design, like every register, every LUT input, every multiplier input, every multiplier output toggles every cycle. So alpha is 1 basically, so then this simplifies to 1/2 CV squared F. So what do you think of their power methodology? Yeah. Do you like their power methodology? Do you have any concerns? Yeah, you. Sorry.
I was wondering if it will result in an overestimation of the power consumption, because I don't think in realistic applications, every single element will be switching in every clock cycle. So wouldn't this 100% signal toggle rate result in them overestimating the power consumption?
Yeah, I think this is pretty pessimistic. I agree with you. So I'm not nuts about this. It's like a simple number. In my opinion, it's not a very good number. It turns out most designs do not, you're right, they don't toggle at that rate. It does vary from one design to another. Your control logic toggles not that much. So there's an old paper from IBM that says control logic toggles at around 12.5%. It's a super simple methodology, but it turns out to be not that far off. Because if you go through like a finite state machine and stuff, it turns out most of the signals in there don't change most cycles. In your data path, which is most of your design, it's harder to say. If you're actually doing a lot of multiply accumulate, then about half your signals are usually changing every cycle. It's kind of like you've got random input data. But random input data, half of the bits used to be 1 and half of them are still 1. So only half of them change with random input data. So that gets you to a 50% toggle rate, not 100. And in a lot of designs, typically it's less than 50% for all sorts of reasons. Maybe you have some muxes that are steering things and so on, and they don't switch that often. If you're doing a lot of multiply, accumulate, and signal processing, then 50% is pretty reasonable. 100% is pretty pessimistic. Yeah?
I actually read the paper, I think yesterday, and I was calculating how much toggle rate an AND gate would experience if you give it independent out inputs with like 50% chance of being 1 or 0.
Yeah.
So you're kind of like, I know it's not like an estimation, but basically, or like a realistic kind of like, it depends on the data set input that you use, but it turns out that if you use inputs that toggle 50%, 0, 50%, 1, and are independent of each other, I think the toggle rate of an AND gate and OR gate is 32%.
Yeah, and that makes sense, because they tend to be, like, their truth table is not balanced, right? Like an AND gate has mostly zeros in its output, and an OR gate has mostly 1s. So you wind up with a bunch of input toggles will not produce an output toggle. So you're right. If you have a lot of decoders, a lot of AND/OR logic, your toggle rate, and that ECE2 tend to have a bunch of those in things like finite state machines and sometimes in MUX networks. They tend to toggle less. Now, the reason I say signal processing, like you're doing multiply accumulate, if you look inside of a multiplier and an adder, there are a lot of XOR gates, okay? And an XOR gate, an input toggles the output toggles, okay? So that now if the 50% inputs are toggling, then your outputs are toggling at 50%. It can actually even get worse if 50% of your inputs toggle and they're going into some multiplier which has got a whole bunch of XORs in cascade. You can actually get glitches. So in other words, internal signals can switch and then switch back as another input changes. So you can actually, your limit for toggle rate is actually not even 100%. You actually can go above 100%. And if you look carefully, if anybody read my lab one really carefully, you clicked on like enable glitch filtering and so on. Some of those glitches are so fast, they don't really happen. Like a digital simulator is simulating and like basically all the events are happening instantaneously. In real hardware, it has inertia. If inside of a multiplier, for example, if two transitions happen really close together, the output doesn't really toggle twice. So that's what glitch filtering is actually doing. It's post-processing the simulator output to remove really fast toggles. Anyway, but the XOR nature of multiply and accumulate tends to produce higher toggle rates. So 50% becomes reasonable. And if you don't control the glitching, like if it's actually a bad design style to take a bunch of multipliers, feed them into other multipliers, without any pipeline registers in between. And the reason is they can actually get glitches, so they're actually all multiplying up the signal activity. Signals are toggling multiple times per second, or multiple times per cycle, and then going into the downstream logic and toggling faster and faster. They'll eventually hit some limit, like the wires just won't swing faster than a certain limit, and that's what glitch filtering does. But it's why pipelining is good for speed. It can also help you with power. On the one hand, it costs you power by adding registers, which take power, but it can also filter out these glitches. So.
Yeah, sorry. Well, one other thing as well is I was thinking because also with assignment 1, what we do is we calculate power by feeding in a test bench with vectorized inputs, and then we kind of like scale that up to the frequency and how much if we were able to copy our circuit, right?
Yeah.
So I was wondering why couldn't they like instantiate like a DSP IP block and just like write a small test bench or something with like vectorized inputs and see that actual activity factor and kind of like, I don't know, do some pessimistic addition on top of that.
I mean, they could have done that. Without a full application, it's hard to get real activities. Like you're right, they could take a DSP block and just send in random data and see what happens. And I think they would have found that they got 50%. So that would be better. In a more complete application, they might get something less than 50%. So yeah, I don't like this 100%. Like it's kind of like, it's not really gonna happen. They should have gone like 50% should have been the upper bound. So all their power numbers for the FPGA are pretty conservative. Okay, but that said, they get the numbers for processors. And what they find here is basically the most power efficient solutions. These are like the GPUs. So they're not terrible for power efficiency, but they're a lot worse for power. They're actually worse for power efficiency than the sort of power optimized processors and much worse than the DSPs. Okay, so the best power efficiency tends to be coming from the DSPs. And this kind of makes sense. So the devices that were essentially targeting a lower throughput and lower power budgets actually did successfully get architectures that were pretty power optimized. So for the FPGAs, how'd they do on compute density per watt? I mean, you see the same behavior, it's maybe even stronger, of if you use smaller operands, like int16, you do a lot better than int32 and a lot better than single precision floating point and so on. So there's a strong push in FPGAs. Try to use the smallest data type that will give you the accuracy you need. And let's see. I guess the other thing you can see here is this is Vertex 6. We go to Vertex 7, which is a process generation better, and all these bars get higher. So going to a better process technology improves your overall performance mostly because you can cram more stuff in the chip, but you might get a little bit of clock frequency too. It also improves your power per computation, which sometimes surprises people. Does that surprise people? Does that seem counterintuitive or it seems intuitive? What do you think?
But I'm just curious, I guess generally before with Bernard scaling, you also sort of maintain your power consumption. But if Bernard scaling then
Yeah, so this is power per operation. So it's not saying that the power of the whole device went down. Effectively, the power per operation went down, right? Dennard scaling was super good. Everything got better, right? Does everybody know what Dennard scaling is? People know what this term is? Who does not know what Dennard scaling is? Okay, so Dennard scaling was true in the semiconductor industry for many, many years. It basically means you scale everything linearly. You make the transistor width like 70% is wide. You make its length 70% of what it used to be. You make the wires 70% as wide, and you drop the voltage by 70%, and you make the gate oxide 70% as thick. It's super hard to do in practice, but the principle of it was super easy. Multiply everything by 0.7. When you do that, you wind up with like your area goes down by a factor of 2, like you have half the area because it goes down quadratically. Your power goes down because you can scale your voltage, and it goes down rapidly, and your performance goes up. Dennard scaling's over. We can't scale basically the gate oxide anymore at the same level, and we can't scale the transistor width at the same level because we get too much leakage, right? So basically, we don't get to do it anymore. We still get benefits from scaling, but not as much as we once did, and it's more complicated. So yeah, but we still do get power reductions going to the new process node because basically the capacitance goes down. Everything gets smaller, so your capacitance goes down. Your voltage usually goes down a little bit. Those two things together give you a power reduction.
But I guess wouldn't you, like at some point, reach like a break-even point where it won't help anymore even if you add more operations on?
It might, but so far it hasn't happened, right? So there's a lot of people spending money to stop it from happening. Someday it probably will happen, but it hasn't yet so far. I guess one of the reasons sometimes people are surprised by this is they've heard that process like static power is going up, right? Transistors are getting leakier as you make them smaller, and that's true. But basically, when you're using a chip to do a lot of processing like that, any well-designed chip, the architect of that chip, there's a paper from Mark Horowitz that basically shows the rough optimal point for total power dissipation is make static power about 30% of your power, and the other 70% dynamic. And you have knobs to control static power. So you can basically increase the threshold voltage of your transistors. You can make the transistor lengths longer. So basically, FPGA architects will do what they need to do to control static power. So they'll still be significant, but they'll make sure it's not out of control. Some of those things they did will actually hurt dynamic power some, but they still get a net benefit, right? Dynamic power goes down. Static power is basically maintained around the same with a lot of effort, and you get a net improvement in power per operation. So we're still getting good power scaling, well, reasonable power scaling as we go to new process technologies. It's just not as good as it once was. Okay, so let me give you a few highlights. So in these generations anyway, the FPGA was about 10 times more power efficient at integer 16-bit operations versus the GPU, and about 5 times more efficient than the CPU. We got the best results at the most advanced process node. So 28 nanometer FPGAs in that plot were better than 40 nanometers. And I just said this, power per operation drops with process shrinks. Floating point, the FPGA gigaops per watt were around the same as the GPUs. The GPU is optimized for floating point. It has tons of hard floating point units. But the FPGA had lower throughput per device. So it was kind of equal on per power efficiency, but worse on throughput. Not in these plots, because it came after this, but ARIA 10 was the first FPGA with hardened floating point units. And the next device after it from Altera basically added a lot more DSP blocks, so devoted a bit more silicon to DSP blocks. So at that point, it could do 9.2 teraflops. And that was comparable to GPUs that are in that same process generation. So basically, once you put hardened floating point units in an FPGA, it seems like it's in the same ballpark as a GPU for single precision floating point. If you don't put hardened floating point units in, then it's not as good at floating point. So maybe that's not a shocking thing. Okay, so that was all about when you're on the chip. What about IOs? So they looked at I/O bandwidth for all of the variations of processors. And they divided into 2 pieces. So the light part is basically memory. Okay, so external memory, so basically variations on DDR. So DDR for the CPUs and DSPs, and for the GPUs, there's something called graphics DDR, which is still DDR, but it basically has tighter timing specs. and use really wide buses to talk to it. So basically, the GPUs have lots of bandwidth to main memory. It fits their execution model where they can tolerate high latency to main memory by having many threads, but they need a lot of bandwidth to keep all those threads busy. And yeah, the other devices don't have nearly as much. The darker part is kind of all the other IOs. So PCI Express, any other network interfaces. So, and basically these devices, well, particularly the GPUs, spend most of their IO bandwidth on main memory, right? That's what they're really optimized for. Okay, so we go to an FPGA. They have a reasonable amount of main memory, but not as much as the GPU. Like they're off by about a factor of 3 compared to what the GPU has. That's not fundamental. Like these FPGAs, you could actually hook them. They have enough IOs that you could actually build a system with these chips that has significantly more memory bandwidth, although you probably would never quite catch up to the GPU or you wouldn't exceed it. But basically in the systems these were in, they tended to focus more of the IOs on everything else, like networking, like Ethernet, PCI Express, et cetera. And they have much better bandwidth on those than any of those other devices. So GPUs really dominate for main memory bandwidth, and they still do, right? So like if you look at, that's one of the things that GPUs have been very aggressive at pushing. Now FPGAs have also increased their main memory bandwidths. They follow some of the same technology trends, but there's still probably a gap of about 3x here. So this basically isn't really changing. GPUs spend a lot of money on external memory bandwidth. FPGAs have more other I/O. So they're used a lot in network processing. They have a lot of high-speed serial transceivers that allow them to do very high-speed networking, PCI Express, et cetera. I think this is just a prompt to myself. I would say like part of this is just, it's not that it's fundamentally impossible to build an FPGA with more memory bandwidth or a GPU with more network bandwidth. It's just the markets have pushed them in these directions. I guess I promise now I'll talk about Blackwell next week. Blackwell is interesting in some of NVIDIA's recent GPUs because they are putting a lot of custom network bandwidth in so that they can link their GPUs together for really large-scale machine learning. So I'd say not for sort of general I/O, but for I/O talking between GPUs. The latest GPUs have also changed this. They now have a lot of bandwidth to talk to other GPUs so that you can distribute a machine learning training or inference across a lot of GPUs. Yeah, so any comments on that? Okay, so I guess the reason I like this paper is I think there's limitations definitely in this methodology, but a simple methodology like this does allow you to do a quick kind of call of, like if you're looking at what should I put something on, getting these peak numbers and seeing is one of these way better than the others could help you like prune the space. It's not going to give you the full picture of what's going to happen, but it could be a useful and not too hard thing to compute. Okay. So now I want to move to like a somewhat different topic. So I've talked a couple times about that there's a high cost to programmability. So the next couple papers are to try to quantify that. And one of them is the other reading from this week. But the first one is trying to quantify the cost of FPGA programmability, right? So an FPGA doesn't have gates, doesn't have just wires. It has these programmable routing and it has lookup tables. And that's going to cost us. Professor Rose at this university did a study in 2007 to try to get hard numbers of how big is this gap in area and delay. So I guess what this is showing is basically they just took a bunch of designs and they're simple designs. So that's one important caveat to keep in mind for this study is these are like really small designs compared to what we would do nowadays. Like, you know, maybe like I think the biggest one's maybe 1,000 LUTs. So they're pretty small. They take them and they run them through the FPGA CAD flow, work out how many logic blocks they take, and then say, well, how much area on the chip is that? And then they take those same designs, run them through an ASIC flow, and see, okay, how much area do the gates and the wiring take? So the gap for the circuits that only have soft logic, so that means they have no multipliers, they have no RAM, all they have is just general logic, is very big. Okay, so they wound up with an average of 35x. So the ASIC took 1/35th the area, so there's a very high penalty for the programmable logic. What do you think the speed gap is? Okay, so it's 35, I think it's 50, 100, bigger. There's no particular reason you would know this, but what do you think? What do you think? You think 2 or 3? So I think it's quite a bit closer. Okay, so 2, 3, 4. So you guys are good guessers, right? Actually, I guess I don't have the, so that's a couple slides ahead. But that's still a good guess. Okay, stay on area though. Okay, but this was, so there's a couple of major caveats on this. So one that's not that bad is for really small designs like this, the ASIC tools can pack stuff really densely. As you make them bigger, they're going to have to space it out a bit to be able to actually fit the metal on top of it. And when they compare to the FPGA, they're basically comparing to an FPGA that has enough routing to route really big designs. So it's a little unfair, but that probably only takes this 35 and maybe move it down to 25 if they actually did bigger designs where the ASIC tools had to space them out a bit. So it changed things some, but probably not that much. The bigger change would be FPGAs don't just have programmable routing and like lookup tables. They have multipliers, they have RAM blocks, they have IOs. So how much, and those blocks are generally much closer to their ASIC equivalents. They have some programmability in them, but not as much, right? So the RAM, you're going to see a lot about how to build a RAM block in an FPGA, but you'll see that the core of it is basically the same as you'd have in an ASIC, and then you put some programmability around that. So it's a lot closer. So when you incorporate those things in a design, how much closer do we get? So basically in their paper they say, well, this is going to depend a lot on how much of that stuff you use. So what they did first is they just took the circuits they had, which are kind of very small and simple. And for the circuits they had, the gap closed some when they include DSPs and multipliers, but not that much. It went from 35x down to 20x. But their designs weren't very good. Okay, so they basically only had a few designs that actually had multipliers in them, and only 3 that had RAM in them. So for a large modern design that you put in an FPGA, what percentage do you think do not have any RAM? 0. Like there is no such design, right? Like if you basically go find like how many designers using FPGAs these days don't use any of the RAM, it's nobody, right? Like that does not exist. So it's kind of, it shows these benchmarks, like, you know, it would have been good to get more complicated benchmarks because only 3 of them have RAM, and they include, basically they say this is a architecture, like this is a design that has hard blocks if it has like 1 hard block. So if I have like 1,000 LUTs and I have 1 memory, that is like a design with memory. So basically these designs look like they're kind of too old, too simple, and they don't really leverage the hard blocks on an FPGA. So the other way they calculated it is they said, okay, well, then the other way you could think about it is you're making a design to go in an existing FPGA, and you're probably going to try to use what's there. And this is pretty common. When people are doing FPGA designs, they usually do look at what am I running out of, and they actually try to use the hard blocks a lot. You often run out of the hard blocks before you run out of other things. So they basically said, well, what if I used all the hard blocks? So I'm a really thrifty designer. I use all the RAM. I use all the DSP. Then how close would I get? And now it gets a lot closer. So in the generation of FPGA they were looking at, it was 4x, which is still reasonably large, but it's a lot better than what the 35x they started at. I think this is probably closer to the reality. They also don't include IOs. So the other thing to realize is that a significant chunk of the area of an FPGA is the IO. If it's a big FPGA, it's maybe 20 or 30%, maybe 30%. If it's a smaller FPGA, it's often 50. The IOs are they're somewhat bigger in an FPGA because they have extra programmability, but they're not that much bigger. So it kind of depends what you're paying for. If you're like paying for a lot of IO, then you get closer than this still. If you're constrained by the compute fabric, then you're going to be more in this range. Okay, but we get a big range here. Okay, so if we're doing like random logic, they got 35x. I'd say that's probably a little high, but 25 or 30 is probably realistic. When you bring the hard blocks in, it could be more like 4. If you don't use all the hard blocks, could be somewhere in between. Okay, so delay gap. So you guys are good guessers. They found the delay gap was 3.5x. Still significant, but not nearly as big. And what do you think? So this was the ones with just soft logic. No RAMs, no DSPs. So they only have a few of those designs with DSPs. But how do you think this changes when you put in the hard logic designs? So you think the gap will go down? Okay. So it doesn't actually move much. Okay. The area moved quite a bit. We saw it actually moved a lot depending on how much hard logic we assumed. The delay gap doesn't vary that much. Does that seem to make sense, or does that seem crazy? So you think it doesn't make sense? Anybody think it does make sense?
I thought the IP blocks were like actually like designed by the FPGA, the designer people to like be as efficient as possible.
They are. The hard blocks are, I mean, you can never say if they're as efficient as possible, but they try hard, right? So yeah, the hard IP blocks are a lot more efficient. What do you think?
It makes sense if you consider that the thing that was the critical path was not the stuff that was replaced by the hard block anyway.
Yeah.
Because we're
Yeah, and so I think these do make sense because they're taking the same RTL and running it through the ASIC flow and the FPGA flow. So yes, the multiplier got a lot faster, but what will happen is there's some logic outside that that becomes your critical path, right? So delay is always a max function, area is like a summation. So, and we actually found this when we put DSP blocks in our chips at Altera. So when we put it in the first Altera chip where we put DSP blocks in, we did find that if you had a lot of multiplications in your design, you got a 10x area reduction on average, but not much delay reduction. And it was for that reason. Your multipliers got way smaller, but if there was some critical path outside there that was limiting you, maybe you got 10% faster before you were limited by that, but then there was some path that was limiting you. There's something that's not shown here, which is if many of your critical paths are gone because they're inside the DSP blocks, then a clever designer might go and look at the remaining paths and might re-optimize them. That's not captured here, and it is hard to capture, right? So maybe with re-optimization, you would bring this down some, but that's a very high effort thing and it's hard to say. So does that make sense? This is a truism though. When you harden things, you usually get big area gains. If people use them a lot, it's actually a lot harder to get delay gains because some other path becomes critical. If you don't speed up all the paths, you don't get the delay gain. Okay, so if I summarize this, we got this really wide range of what's the FPGA versus ASIC area gap. 4x if you use lots of logic blocks, 35x if it's all soft logic and you're comparing to a super dense ASIC. So I guess I already mentioned this. I think this is a little bit optimistic for ASICs because their small designs meant they didn't have to space anything out to make it routable, and usually in a larger ASIC you would have to. But that still would leave you with like a range of 4x to 21x. So it would still be a pretty wide, if it was all soft logic, it would still be pretty bad. The ASIC speed versus FPGA speed was around 3x. So area times delay is like a measure of silicon efficiency. If I want to get more performance out of a system, I can do more parallelism. And the smaller my area, the more parallelism I can get. Or I can clock it faster. And the smaller my delay, the faster I can clock it. So area delay is essentially like inversely proportional to throughput per unit of silicon, right? So I would like this to be as small as possible. And if I care about throughput, this is the number one thing I want to minimize, right? It correlates very well to the inverse of throughput that I can get in a parallel execution system. And it looks not great, right? 12x if I use lots of hard blocks, 60x if I didn't use many hard blocks versus an ASIC. A more recent study that was done by Andrew Boutros, who did his PhD here, but is now at Waterloo, he looked at a bigger system. So he looked at convolutional neural network accelerators implemented on FPGAs versus ASICs. So they have a realistic amount of hard blocks. They fundamentally use a bunch of memory, a bunch of logic, a bunch of multipliers. And what he found is that the area gap was 8x. Okay, so it's not 4x, but it's closer to that. And the delay gaps were still pretty big, about 4x. These gaps are to a non-programmable ASIC. right? So in the FPGA accelerator, he can make something that just does CNN acceleration for this class of networks, and he compares to an ASIC that is exactly the same design. That ASIC would be very risky to make because it has very little programmability. The FPGA still has programmability. You don't have to make a custom part for it. So this is a good estimate of what you get in terms of the substrate efficiency, but there's a business model here of like, you probably wouldn't want to make this ASIC. What you would probably want to do is make an ASIC that had a bunch more programmability in it so you could sell it to a wider market. But that's very hard to quantify. The other thing to consider is that the average ASIC lags an FPGA in process technology because of the fact that its market is smaller. Right? This is not true for like NVIDIA's GPUs. Their market is like enormous. So they are like on the absolute cutting edge of process technology. But if you're making like more special purpose ASICs, they tend to not go to the cutting edge. They're not like in 3 or 5 nanometer because it's just too expensive and too time consuming. So historically, this was by 3 generations, okay? I don't know if it's exactly 3 generations now because Moore's law is slowing down some, so maybe it'll compress a little bit. It's hard to say. That's actually a big difference. If you're actually comparing, I buy an FPGA, and I'll probably, if I got a fairly big design, I'll buy one in the latest process node usually. That's usually the best deal. Versus I'm going to make an ASIC, but I can't make it in the latest process node. It's too expensive. Going back 3 process nodes, that's an 8x density loss, right? You get about double the density every process node. So 2 to the third is 8. Speed is not going up as much, but it is going up 10 or 20% anyway per process generation. So that's probably a 1.5x or more speed loss. So that is worth 12x area delay. So if you now compare buying an FPGA versus making an ASIC in the process that you can probably afford, it's a lot closer. You're now maybe 1x to 8x in terms of your area delay gap. This is actually more like the business calculation that people are usually making. Because otherwise you'd go, if you start off with this 35x, you go, why would I do that, right? 35x area and 3x delay is just too much. Yeah?
Plus with like a new process, if it's like your first time using it, like there's going to be loads of like debugging and stuff to do when making an ASIC versus like a more mature node where maybe your tools are mixed up.
Yeah. So if you go to a more mature node, the tools are somewhat cheaper. The design is not as complicated. There's less risk premium. The masks are cheaper. It does bring your cost and your risk down some. Still going to have a lot more NRE than putting it in an existing programmable part like an FPGA.
Yeah, so it's like an event that you use.
Yeah. Okay, but this was like part of like trying to figure out the cost of programmability. So what's the cost of an FPGA's programmability versus just building it out of gates and wires like in an ASIC? So the other way you can get programmability, if you're not using an FPGA where you have this low-level hardware programmability, is in your programming model. Have an instruction stream. And that's what the paper that you were to read last week talked about. So how many people read this paper, actually? So it's pretty good. So any thoughts on it? Did you like it, not like it? What do you think?
It feels like why would you implement a soft vector processor when I guess you can just stick a hard one like next to the FPGA die?
Yeah, I mean, if you have a hard one, you're right. Then you probably wouldn't build a soft one until you run out.
It's a nice comparison. Oh, let's see how like when you improve this vector processor, what's going to happen if you're just implementing hardware. But again, why would you ever do that when you stick on a hard processor, which is what most FPGA vendors do nowadays?
Yeah, so you're questioning kind of like how big a role is a niche is there for a soft vector processor on an FPGA. I mean, I think you're right that there's, well, I believe that Microchip actually has one. So why don't you tell us?
Yeah, so like when I read the paper, my thought process was more like, as a hardware engineer, I have an easier time making hardware out of the problem than I would have to like express it in terms of their niche vector assembly language, because that just requires you to write assembly language. That's what this says. To use this specify, you need to write out an assembly. No compiler is gonna bring out the pattern for you.
Yeah. No, I think that's a good point. So one of the people who worked on the Vespa and his follow-on projects is Guy Lemieux, who's a prof at UBC, who actually created a company called Vector Blocks to commercialize it. with some success, but I think not complete success. They ultimately sold the company, so I think they had some level of success, but I think they had exactly this kind of challenge of, okay, it's not as efficient as a hard vector processor. Okay, so that is your competition. It's also not as efficient as if you built the sort of, say, streaming or specific hardware in the FPGA. So they had to try to convince the customer base that it hit some sweet spot in the middle, right? Like that it was more configurable than the hard vector processor you could buy off the shelf and was good enough in performance compared to the hardware you could build in the FPGA. I think they managed to convince some people of that, but it wasn't the majority, right? Because I think that was their challenge in growing the market. So I think that's a good observation.
Like RISC-V now has like configurable vector lengths and the vector essentially, for instance, like if I'm
Yeah, so and actually guys on the standards committee for that. So some of this work that they did probably is finding its way into RISC-V. That's, I would say, not an argument against like Vespa though, because that's just an argument of like, if you brand it as RISC-V, then now I like it. Do you know what I mean? So, and there's some truth to that. Like you have an ecosystem, right? Once you have an ecosystem, there's momentum behind it. I guess you still have the question of like, should you do that RISC-V hard or soft? Like if you put a hard RISC-V vector processor in the FPGA, it's always going to be more efficient. I guess their argument, this is now Vector Blocks, like Guy Lemieux's company. Their argument was essentially like maybe your system has enough customization that, like again, like maybe I'm talking to custom IOs and all sorts of things that I need to be in an FPGA, and then I don't want to build the hardware by hand. I think a vector processor would be faster. So that was the argument. I think they convinced some, but I think there were lots that went, no, if I'm in an FPGA, I'm okay making the hardware. So, and if I'm okay with vector processors, then I'm going to look hard for one that basically is already existing. But what I really like about the paper is the fact that it does a head-to-head comparison of just programming model. Like it's isolated sort of one variable. Because they build everything in an FPGA, the only thing changing as they go from essentially hardware units, so like streaming hardware units, to a scalar processor, to a vector processor, the only thing that's changing is essentially the programming model, right? They're never changing the implementation. So I think the first order, all of the ratios would probably still apply if they did it in an ASIC. Like we can't prove that, but they're just trying to isolate that one component. So what's interesting is that the cost of a scalar processor, which again has to fetch instructions, decode them, control this fixed data path, store temporaries, route them back through again, like it's very large. So for a scalar processor that does one thing at a time, it's 432 times slower and 6.7 times larger than just building hardware that does that one computation. So if we multiply that out, we get 2900x the area delay. So 2900x efficiency loss, which is huge, right? But people still buy scalar processors because there's still this huge advantage of if I buy a processor, I didn't have to make that custom hardware. So I'm not saying that this means don't buy a scalar processor. It just means you did give a lot up when you did that. If they use a vector processor, so now they start using SIMD, it does get significantly more efficient. So this gap drops to 25 times slower, but it gets bigger. That makes sense, right? They get more execution units. So it's 36x larger, but 25x slower. It helps the area delay by quite a bit, factor of 3. So it goes down to like 900x area delay. And they evaluate different SIMD widths, and they find their best trade-off was an 8-way SIMD for the applications they did. So if there's enough parallelism, it shows a vector processor is a much better choice. But even then, it's got a large overhead from its programming model. Okay, so this is like me trying to put all these numbers together. Okay, so if I take an ASIC and I make just hardware in it, so say streaming hardware or some other hardware unit that just does one thing, I'm just going to call that 1 for area delay and area times delay. And I'm never going to beat that, right? If I take that same design and I put it in an FPGA, so my area, we just calculated, if we use lots of hard blocks, it's 4x worse. If we use lots of soft logic, it's about 21x worse. Our delay is about 3x worse, so our area delay is 12 to 60x worse. If I make an ASIC, but I can't just make the hardware because I'm worried. I can't make this ASIC for just one narrow market and I can never change it. Like what if something changes? So I'm not going to do that. I'm just going to go buy a scalar processor. So that scalar processor is a hard processor. It was made as an ASIC, but I can just buy it. So its area is big, area is, I got this wrong actually. This is, oh no, its area is 6.7x worse in area. Its delay is 432 times worse because it needs many cycles, right, to calculate everything. So area delay is really bad, 2900x. Vector processor, do it in ASIC, so it's hardened, gets better. So 900x the area delay product. So if I just now go, okay, well, I can't afford to make like a hardwired ASIC for this application. I need something programmable. My best choices now become this, right? So I buy somebody's vector processor, or this. I buy somebody's FPGA. And if I compare those two numbers, so, and there's going to be a wide range based on application. So I'm not trying to give you these numbers as like, you know, these are highly precise. But basically, the area now of the FPGA is, you know, maybe a little better to maybe 6x worse, right? So still a pretty broad range depending on how well we use the hard blocks. The delay of the FPGA is better, right? So the vector processor is 12x slower. The area delay gap is actually pretty big, but now in the FPGA's favor. So 9x to 75x. Okay, so again, I'm going to say these are like numbers that you're not going to put in a paper and say like, you know, this is accurate to two significant figures. But I guess the point of this is you have these huge programmability penalties. So there's a really big programmability penalty to use an FPGA, but there's also a really big programmability penalty to move to a processor style. So if you need programmability, you kind of wind up with these two choices. Use a processor and give up lots on the instruction fetch decode cycle, or use an FPGA and give up lots in the programmable routing and the programmable logic. But for a lot of applications, the FPGA winds up being more efficient than even a vector processor, okay? You can't say that for all applications. If I have an application that is all single precision floating point on huge data sets, then there is a GPU, which basically is a programmable ASIC that was optimized for exactly that, and that it's going to be hard to beat that, right? But if you're using a more generic vector processor, your hardware is a little more specific, you can often win by pretty large margins. If you look at in this paper, you'll see that there's a wide range of results they get on different applications too. So, you know, the bit widths you use matter a lot, right? FPGAs like narrow data types. The operation types. If you have unusual operations, that's very good for an FPGA because they have to be synthesized out of a bunch of processor instructions. The amount of parallelism matters, right? If there's almost no parallelism, then the FPGA is not going to get this speed up versus a scalar processor. And memory access. If you were limited by off-chip memory, then a lot of these speed gains would get washed out. So there are a lot of application-specific things. We're just kind of taking the average results from this paper and blending it together. But you'd have to look at those for your specific application. Okay. So for that paper that many people read, I guess the part I liked about it was this, trying to use it to infer things about the efficiency of a processor-based model. But what's that? No, they built everything on an FPGA, right? But that's what I liked about this is because they essentially factored out like how did I build it. The only thing they're changing is essentially the programming model, right? Does that make sense? I mean, you could do the same thing by building everything out of an ASIC, but people rarely do that because it's so expensive. Like, it'd be like, I built the following incredibly specific application in an ASIC. I can sell it to no one. You know, for highly specific applications, that usually just doesn't make any sense. You have to add back in, like take a GPU. It's a form of ASIC, but it has a ton of programmability in it still. So any limitations or caveats you'd put on this? Or did I just totally convince you? You got it. It's like, it's those numbers. Yeah.
This is just paper specific. It's not about like best class. I think when I was reading their benchmark or like their the metric, how they generated the benchmarks or the metrics that they got, I found their methodology to be a bit like, I wouldn't say ideal because I think so for the scalar processor, for example, they got the number of cycles it takes to execute one benchmark by putting that on a Stratix 2 FPGA. Mm-hmm. But then they got the Fmax and the area by implementing on a Stratix 3 FPGA. Mm. And for, I think the Vespas, they did something similar by factoring Altera to get the silicon area efficiency for Stratix 2 and then mapping it to a Stratix 3 architecture.
Oh yeah, I know. I'm the one who gave them that data. So I know that data. So the reason they have, like, so I like this work actually. I suggested like, Peter, I knew Peter Anacors's work on some other papers, and I suggested, why don't you do a direct comparison? So he did this. That's part of why I like the paper. I was like, I want this direct comparison. He went away and did it. They needed the area, yeah, for both this study and for the Jonathan Rose study, they needed the area of logic blocks, right? Actually, I can't remember if it was this paper. It was another one Jonathan wrote. So I gave Jonathan the numbers for what were the areas for a Stratix 2 logic block and, actually no, Stratix 2 got from someone else. Sorry, I gave him it for Stratix 3. So you're basically saying he used the numbers for Stratix 2 and just assumed they'd scale to Stratix 3? Yeah.
Extrapolated it to a Stratix 2. So my one question is like, why not just normalize it across one device, get all the measurements on that? I think it will make like the data like a bit.
Yeah, that's a good point. It makes it a little more confusing if they're doing things in between. Yeah, they probably had some problems of like these numbers are, like the areas of blocks are pretty secret. So the numbers for Stratix 3, I basically gave to Henry Wong. So they're published because I gave him the numbers. And then lots of people refer to that. And basically I remember I was co-supervising Henry Wong, and I was also at Altera, and he basically needed these numbers. And I was like, who do I ask for approval? I went, I think I could approve this. So I self-approved release of the numbers. So you should maybe pause that. Anyway, but for most devices, it's just not known. So, but it's a good point. So I have to go back through it, and maybe they could have cleaned up their methodology some. Any other? I mean, I have something that I think is important. Yeah.
Right. So I don't know if this one is completely valid, but the paper mentioned that we're using embedded workloads to do the benchmark, right? And in embedded applications, we're really concerned about power consumption. And since this was doing a comparison between LESPA and hardware and ASICs, I was wondering why there was no analysis on the power consumption of the various implementations.
Yeah, it's a good question. It would be a nice thing to add to the paper, so it would be good to have that. So I agree with you, and I guess we can't answer what the power of comparison would be. Dynamic power to first order correlates with area, but that's not a perfect correlation. So it would be nice to have in here. I guess it's not really a criticism of the paper, it's just an important limitation, I'd say. It relates to benchmarks as well. So if you look at their benchmarks, they have operand sizes of 1 bit. I think that was the Viterbi decoder, 8 bits, 16, 16, 32, 32, all integers. Their data varies a lot. Like operand size matters a lot. So at an operand size of 1, right, nobody builds a 1-bit wide data path in a processor because your instruction overhead is unbelievable, right? So hardware units are clearly going to just be extremely efficient when you're building like 1-bit wide data. So it's a real benchmark. But it's maybe important to understand that there's a much more capacity for gain here than here. So this overall average blends a lot of things together. The 1 and 8-bit data paths give them a big advantage versus the 32-bit. And there are lots of systems that actually do have, well, for example, Viterbi decoding of 1 bit at a time is a real thing. So you wind up with a big gain there, but it won't translate to everything. So basically, as the data types get bigger and more complicated, you're going to wind up with it's going to amortize the cost of the extraction, fetch, et cetera, in a processor. So the overall average is probably hiding like a fair amount of variation across benchmarks. Okay, so they did a scalar comparison and a vector processor comparison. So which one do you think is more relevant to like today's hard processors? What do you think?
I guess the vector processor is you're trying to extract more synergy stuff with the type of nature of applications that are becoming more and more important.
Yeah, I agree. So all the applications they choose are ones that would be logical to implement in an FPGA, meaning they have parallelism, which means they also map better to a vector processor. And nowadays, every major processor family has vector options, like either they built SIMD in or it's an option in RISC-V. So that's the number you'd want to focus on, because if you got data parallelism, you probably should not be using a scalar processor if you want high throughput. And that's it for today. So if there's no questions, we're done for today. If you have any questions, come up and ask me. I'll be around for a while.